Hi, complete lesson on oscillation focused on Edexcel IAL Unit 5 syllabus. Okay, what is oscillation? Oscillation means repeated movement or repeated motion is called oscillation. There are examples, many examples we can tell for oscillation. For example, if you attach a small sphere to a like a string and let it just push it to a small distance and leave it, it will oscillate, it will show oscillation. Like that, even if you have a spring attached to a mass, the spring will be at rest, which is carrying a mass, then pull it through small distance and leave it, then the spring will oscillate. Repeated movement it will show. Same way, when a spring attached in horizontal position to a trolley or something like that on a table and pull this trolley through a small distance and leave it, then it will oscillate. Not only that, even a small object, something like a test tube, a weighted test tube floating in water, so it will be at rest. Push the test tube through small distance and leave it. The test tube which carries a small mass inside, that will perform oscillation. So like that, there are many different examples we can show. Even bungee jumper he also can perform oscillation. So like that, there are many different examples we can tell or show for oscillation. That means oscillation means repeated movement is called oscillation. Okay, so there we use different technical words. First thing you must know, equilibrium position. So the equilibrium position means the position at which the resultant force, any system that when it performs oscillation, there will be force acting on it. Not only one force, there could be different forces or more than one forces acting on it. So the position at which the resultant force acting on it becomes equal to 0 is called the equilibrium position. Or we can say the position to which it comes to rest when it is not oscillating is also the equilibrium positions. Either way we can show, but the better way of telling what is equilibrium position means position at which the resultant force acting on the oscillating system becomes equal to 0 is called equilibrium position. So when the system is not oscillating, it will come to rest at the equilibrium position. Then you should know what is oscillator. Oscillator means the system that performs or shows oscillation is called oscillator. Earlier I drew different diagrams. For example, a spring which is carrying a mass, or a spring in horizontal position which is attached to a trolley or test tube which is floating in water. Each of them are different oscillators. So oscillator means a system that performs oscillation is called oscillator. Okay, so you know the meaning of oscillator, you know the meaning of equilibrium position. The next thing is time period of the oscillation. What do you mean time period of the oscillation means? The time taken to complete one full oscillation. Okay, what is one full oscillation? For example, I'll take an example like a simple pendulum. We call a small bob attached to a string. Okay, it is the equilibrium position because it will be at rest at this position when it is not oscillating. Okay, so then pull it and leave it to the left or right. You can pull it to the right or left. Okay, for example, you pull it to the right. Okay, it has come to this position now. So from this, when you leave it, it will move from here to here. Then it will come back to this one. This is called, the time taken for this oscillation is called one period. Or if I consider from the equilibrium position, you are consider the motion. So here I consider the motion from the extreme position. Extreme position means where it has gone to the maximum position, that we call extreme position. So from there, when I consider the time taken to move from this extreme position to the other extreme position, then come back to the same initial extreme position, the time taken for that oscillation is called time period. We call this as one full oscillation. Same way, if I consider from the equilibrium position, so the time taken to move from here to the one side of the extreme position, then from here to the other side of the extreme position, then come back to the same initial point, that is the equilibrium position. This is called one full oscillation, and the time taken for this oscillation is the time period. Okay, so you must know the meaning of time period also, and you should be able to identify one full oscillation. Even if it is like a spring attached to trolley on a horizontal table, when you keep it like this, it will be at rest at this position. So you pull it to the right. So from here you pull it to this side and you are leaving it. It will move from here to this extreme position where the spring will be compressed. Then it will move back to this position. So the time taken for this oscillation is the time period, and this oscillation is called one period. The time taken for that oscillation is called time period. Like that, you must be able to know the meaning of one full oscillation, and the time taken to perform one full oscillation is called time period. It can be any unit. The notation is capital T. Okay. The next thing you should know is frequency of the oscillation. Frequency of the oscillation means number of oscillations completed during 1 second. Normally we consider 1 second, or you can say during unit time, but normally we consider 1 second. So the number of oscillations completed per second is called, or is defined as, frequency of the oscillation. That need not to be a whole number. It could be 2.3 or something like that. Also, it also correct. We can say the frequency. So frequency means number of oscillations completed per second is defined as frequency. So its unit is per second. Base unit. SI unit is hertz. And also, you learned that in waves also, the period and frequency. The relationship between period and frequency is T equal 1 over F, or F equal 1 over T. The same relationship we here also use to relate time period and the frequency. Okay. Then displacement. Okay, what is displacement during oscillation? Displacement means it's always measured from the equilibrium position. Displacement is a vector quantity. You learn that even in year 10, even in unit 1. Displacement is a vector quantity. But here the displacement is measured from the equilibrium position. Careful. It's a very common mistake students they make when we consider the displacement. Displacement is measured from the equilibrium position. So if I consider oscillation something like this, okay, consider this diagram. A sphere is kept on a smooth horizontal surface, and it's attached to a spring. O is the equilibrium position. So equilibrium position means the position at which the resultant force is equal to 0. So from this position, if the spring is compressible, right? From this position, the sphere is pulled to the right up to this position. Name it P1. The sphere is pulled up to here, then released. So we'll take, this is the time t equals 0 at which the sphere is released. Okay, the sphere will move towards the equilibrium position because the spring will pull it back due to the tension. The sphere will move towards the equilibrium position. So initially when t equals 0, what is the displacement? The displacement is measured from the equilibrium position. It's measured from the equilibrium position. Okay, the displacement is measured always from the equilibrium position. So later, when the sphere comes to this position, it has come to this position. So at time t equal t1, the sphere has come to this position, t equal t1. So what's the displacement at t1? We use the word at t1, that is not earlier one. Say if I say earlier it was S1, now at time t, or if I say the initially x naught, initially when t equals 0, the displacement is x naught when it is at p1. Now it has come to the position p2 at time t equal t1. At time t equal t1, it has come to the position point p1. So what is the displacement means? It must be measured from the equilibrium position. So it should be written this way, that is x1, not this one. We don't measure the displacement from P1 to P2. We measure always from the equilibrium position, because here we say displacement at. You can see that later when I start simple harmonic motion, the equations are displacement at. We don't consider displacement during the time. We don't consider displacement at an instant. What is the displacement? Okay, so here the simple harmonic motion, I haven't defined it. I'm going to define. Define means the conditions required to have a simple harmonic motion. But anyway, whatever it is, in your syllabus, always, not only your syllabus, during this simple harmonic motion, we always consider the displacement at an instant, not the displacement during the time period. Say for example, if I say initially this x naught, for example 10 centimeter when t equals 0, later when this x1, for example 4 centimeter. So what is the where the time taken t1, maybe I can name the time maybe 2 seconds. Okay, so I can the displacement initially when t equals 0 is 10 centimeter, displacement at 2 seconds is 4 centimeter. But if you ask a student who is doing unit 1, what is the displacement 2 seconds, don't say at or during, he will say certainly initially the sphere was at P1, now it has come to P2, then he will say the displacement is 6 centimeter towards left. But actually here we will say the displacement at 2 seconds, is 4 centimeter towards right. It's moving towards left. Actually you can see the motion is towards left. When you release it from P1, it's moving towards O. But we say at 2 seconds the displacement is 4 centimeters towards right, because we measure always the displacement from O. We take it as a reference point O, and we consider the displacement at, not the displacement during that time we don't consider. Okay, this is the displacement at. So this is a little bit confusion, but anyway, that's the way the equations we are going to get later. You would have done it at school. That equation also always gives the displacement at a particular instant. Okay, that you must know that. Okay, so the next thing is amplitude. Amplitude means during the oscillation, it must be, when we consider simple harmonic motion, the oscillation must be symmetrical on either side of the equilibrium position. That's the way your syllabus. You won't get any question where the amplitude varies or anything, you won't get. So we consider the oscillation symmetrical on either side about the equilibrium position, and the maximum displacement is called amplitude. So amplitude could be denoted by either capital A or x naught. Either way we can use for amplitude. Sometimes certain books they use capital A for amplitude. Some books they use x naught for the amplitude. Okay, in your syllabus we use capital A to indicate amplitude. Amplitude is the maximum displacement. Okay, so the next thing is simple harmonic motion. What is the meaning of, or what's the condition for simple harmonic motion? All the oscillations won't be simple harmonic. To be a simple harmonic motion, certain conditions must be satisfied. What are the conditions that must be satisfied if an oscillation wants to be simple harmonic? You must know that. So the first condition is the displacement. I already told that displacement is always measured from the equilibrium position, so it's a vector quantity. If I take towards right positive, towards left should be negative. Or if I take vertical oscillation, upward direction positive, then downward direction from the equilibrium position should be negative. Always we measure from the equilibrium position, and displacement is a vector quantity. It has direction, right? Okay, so you know acceleration also a vector quantity, so it also has direction. So the first condition, if an oscillation wants to be a simple harmonic motion, the first condition, the acceleration must be directly proportional to displacement. So it can't be a constant acceleration. The acceleration is depending on displacement, and it must be directly proportional to the displacement. The second condition, the direction of the acceleration should be always point directed towards the equilibrium position. Say for example, imagine this is the equilibrium position. A particle is oscillating. The oscillation is due to the motion or oscillation of a particle. A particle is oscillating on either side of P and Q. So P and Q are the extreme position. O is the equilibrium position. A particle is oscillating on either side. So if the particle is here, and if the particle is, whether it's moving towards O or moving towards Q, we don't care. Whatever the direction of motion, the acceleration must be directed towards the equilibrium position. acceleration must be directed towards the equilibrium position. And we know that displacement is always measured from the equilibrium position. So the displacement is measured from here, x. You know that x is going to be opposite to the direction of x is opposite to the direction of A. Same way, when the particle is on the left side of the equilibrium position, there also, whatever the direction the particle moves, we don't care, but the acceleration must be always towards the equilibrium position. So if the acceleration is always towards the equilibrium position, the displacement is always measured from the equilibrium position. Means here also you can see the direction of the displacement and the direction of the acceleration are in opposite. So whatever the direction of motion the particle oscillates or the system oscillates, we don't care. The direction of the acceleration must be always directed towards the equilibrium position. And I already told that the displacement is always measured from the equilibrium position. Therefore, always the direction of the displacement and the direction of the acceleration will be opposite among them. But the direction of the acceleration and direction of the displacement opposite among them. At the same time, acceleration must be directly proportional to the displacement. So when two vectors are always opposite, how do we denote? We denote it with minus sign. So that's the reason we write this like A proportional to minus x. So the minus sign indicates the direction of acceleration is always opposite to the direction of displacement, or direction of displacement is always opposite to the direction of acceleration. Okay, so you know that if an oscillation wants to be simple harmonic, the oscillation should satisfy two conditions. What are they? The acceleration must be directly proportional to displacement, first condition. The second condition, the direction of the acceleration must be always towards the equilibrium position. So one by one we'll analyze certain examples and find out whether can it be a simple harmonic motion, or can it perform a simple harmonic motion, or can that oscillation be a simple harmonic motion. We'll analyze one by one. The first one, we'll imagine two ramps are kept like this. Imagine two smooth ramps are kept as shown on the diagram. They make the same angle, so perfectly smooth, no drag force, no friction. If you keep a small sphere, something like a ball bearing, and release it, what will happen? According to the law of conservation of energy, there is no drag force, no loss of energy. So the ball bearing will accelerate downwards. When it comes here, it will have the maximum speed, gaining kinetic energy, loss in GP, gaining kinetic energy. So it will move to this side. So when it moves to this side, it will come back to the same level, because both sides it has the same angle. Both ramps are making the same angle. So the sphere will move, the ball bearing will downwards accelerate, then decelerate, then accelerate, decelerate, like that. Since there is no drag force, no loss of energy, it will oscillate forever. Okay. So can this oscillation, so it's an oscillation, it's repeated movement. The ball bearing is going to move repeatedly between this point and the same level. We can imagine the point, this is P1 to P2. So if I consider same level somewhere here, P2 is going to oscillate between P1 and P2 continuously. Okay, can this oscillation, so this is the equilibrium position, because when it is not oscillating, it will come to rest at this position. So that is going to be the equilibrium position. So I can name the lowest point of the two ramps where they are touching each other. That is going to be the equilibrium position of this oscillation. Okay, can this oscillation, this we can say an oscillator, the whole system can be taken as an oscillator. Can this oscillation be a simple harmonic motion? We'll analyze it. Okay, so no friction. If I think about the ball bearing, it has mass. It's kept on a ramp at this position. So the mass is m. It makes an angle theta with horizontal. So the component of the weight along the ramp down is mg sine theta. mg sine theta. So when I consider the equilibrium position, this is the equilibrium position. I already explained why. Because when it is not oscillating, it will come to rest at this position. So mg sine theta is pointing towards the equilibrium position, mg sine theta. So if I use the Newton's second law, F equal ma, that is mg sine theta equal to ma, so the acceleration is towards the equilibrium position, which is g sine theta. Same way, after it passes the equilibrium position, it's going to move to the left side until it reaches the point P2. There, the velocity is from O to P2, but the acceleration is due to the component of the weight. When the sphere is here, the component of the weight here also will act towards the equilibrium position, that is mg sine theta. So there also the acceleration will be towards the equilibrium position, which is a is equal to g sine theta. Okay, so the acceleration is whatever the direction of motion the sphere or the ball bearing performs, or in whatever the direction, either left or right, the acceleration of the ball bearing is pointing towards the equilibrium position O. But can this be a simple harmonic motion? So here also the acceleration is always directed towards the equilibrium position. But can it be a simple harmonic motion? Because here the acceleration is directed towards the equilibrium position. But when you consider the acceleration is constant here. G is constant, theta is constant, sine theta is constant. So here acceleration is directed towards the equilibrium position. Whatever the direction of motion, the acceleration is always pointed towards the equilibrium position, but acceleration is not directly proportional to displacement. It is a constant. The acceleration is a constant acceleration. Therefore, it is not a simple harmonic motion. It's an oscillation, yes, where the acceleration is always directed towards the equilibrium position. You know that to be a simple harmonic motion, two conditions should be satisfied. First, acceleration must be directly proportional to displacement. The second condition, the acceleration must always point towards the equilibrium position. This oscillation is satisfying the second condition, it's pointing towards the equilibrium position, but acceleration is not depending on displacement. Acceleration is a constant here, therefore this is not a simple harmonic motion. Okay, so all the oscillations are not simple harmonic. The conditions must be satisfied. I already told several times. A proportional to x, acceleration directly proportional to a displacement, that is not satisfied here, but the second condition is satisfied here, therefore it won't be a simple harmonic motion. Okay, now I'll draw a few examples, more examples, and we'll check whether that type of oscillations, can they perform a simple harmonic motion. Okay, we'll consider this second example. Spring which has spring constant K, and the spring is compressible. You can compress the spring. So that such spring is attached to a trolley of mass m and kept on a frictionless horizontal surface. So initially the trolley is at equilibrium position O. You pull the trolley towards right through a small displacement and you release it. So when the trolley is on the right side, I'll draw it here, when the trolley is on the right side, what are the forces acting on it? So this is the equilibrium position, and draw a vertical line for the equilibrium position. So what are the forces acting on the trolley? The weight is acting downwards, mg, and the normal reaction from the surface is acting up. So R equal mg, they balance each other, we don't need it. Okay, the spring is extended. So spring will exert a tension on the trolley, that is towards left. We know that, we learned that tension is directly proportional to extension according to Hooke's law. So T proportional to extension, that we know that T is equal to Kx. Okay, so the displacement is measured from the equilibrium position. So the displacement is measured from O towards right when the trolley is here. When the trolley is moving to the left or right, we don't care, but that's nothing. But it's not a matter, but we measure the displacement from the equilibrium position, that is towards right x. The only force that performs the oscillation or motion is the unbalanced force which is the tension, because R and mg balance each other. So the only one unbalanced force is there, that is T. So the T is acting towards left. You can see the T, the tension, which is the unbalanced force, acting towards left. So according to F equal ma, when we consider the tension is towards left, that is Kx, F equal Kx is equal to ma. So A equal K over m into x. Look at here, k is a constant, m is a constant. So k is a constant, m is a constant. So a equal a constant into x. Therefore, a proportional to x here. The acceleration of the trolley depends on the displacement, or the displacement is measured from the equilibrium position. So actually x is both displacement as well as the extension, both measured from the equilibrium position. Now, so a proportional to displacement x here. At the same time, you can see that the direction of the displacement is towards right, the tension is towards left. Therefore, always the direction of the tension or the direction of the force, that is always force and acceleration are parallel to each other. Resultant force and acceleration are parallel to each other according to Newton's second law. The direction of force, the resultant force and the acceleration are parallel vectors. So the resultant force is towards left, means acceleration is always pointing towards the equilibrium position. You can see that acceleration is always pointing towards the equilibrium position, because tension is always pointing towards the equilibrium position when the trolley is on the right side of O. Okay, if the trolley is on the left side of O, the spring will be compressed. So when the spring is compressed, I'll draw the trolley here. When the spring is compressed, the compressive force will act on the trolley. That will be towards right. The compressive force, that also tension, that is acting towards right. So we know that T equal to Kx. X is the displacement. And also that will be the compression of the spring, that is measured from the equilibrium position. From O, it's measured towards left, x, that is the compression, as well as that is the displacement also, because only one spring is attached to the trolley. So the compression or the displacement is towards left. The tension, which is unbalanced force, is acting towards right. So here also the direction of the unbalanced force is opposite to the direction of displacement, means direction of acceleration is opposite to the direction of displacement. Also the tension is pointing towards the equilibrium position, therefore acceleration also will point towards the equilibrium position when the trolley is on the left side of the equilibrium position. So here T equal Kx, same way I can derive here also F equal ma. So instead of T, that is Kx equal ma, A equal K over mx. When it's on the left side, K and m are constants, so the whole thing is constant. So A proportional to x. Also A is pointing towards the equilibrium position, because tension is pointing towards the equilibrium position. So this will perform simple harmonic motion. So when you attach a trolley or sphere or whatever, any mass to a spring, and when the mass is kept on a smooth surface and when you let it oscillate, that oscillation will be simple harmonic. Okay, so we'll consider this type of oscillation. A spring is attached to a trolley and the trolley is kept on a smooth ramp that makes an angle theta with horizontal. This is the position we call equilibrium position. The trolley is at rest. When the trolley is at rest, already the spring is extended, because you know the component of the weight of the trolley along the slope down is mg sine theta. To balance that downward component of the weight, there will be a tension upwards acting on the trolley, so that tension will balance the weight of the trolley along the slope downward. So when the trolley is at equilibrium position O, there is, when I draw the free body force diagram separately, something like this. So the weight will act vertically down, mg, that we don't need. The component of the weight along the slope down is mg sine theta, that is balanced by a tension, and that is T. We can say the extension of the spring due to this force of mg sine theta is x1. So T is equal to kx1, where k is the spring constant of the spring. So we can say kx1 is equal to mg, because it's at O, where the resultant force acting on the trolley is 0. There's a normal reaction. We don't need the normal reaction. We don't consider that in this oscillation. So R is balanced by mg cos theta, what you learned in unit 1. So here kx1 is equal to mg. Then what we do, from this position we pull the trolley through a small distance. you know O is the equilibrium position, so you are pulling it down through X. I am not drawing the trolley again, so but you are pulling it towards right through X and you leave it. So trolley is going to oscillate between this point, we can call P1, that point as P1, and P2. Between P1 and P2, the trolley is going to oscillate. The spring is compressible. You can compress the spring a lot. We'll take that way. The turns of the spring won't hit each other and stop the oscillation. The compressible spring. So the spring is going to oscillate. The trolley is going to oscillate on either side of O up to P1 and P2. So when the trolley is somewhere on the right side at a displacement x from O, that time the extension of the spring is x1 plus x. So when we consider that situation, if I draw the diagram again, when the trolley is at a position before P1 somewhere, when it has a displacement towards right, x from the equilibrium position, the extension of the spring is going to be x plus x1. Already it has extension x1 when it is at O. Now the extension is going to be x plus x1. So the tension will act on the trolley along the slope up, that is k into x plus x1. The component of the weight will be along the slope down mg sine theta. Okay, so we know that kx plus x1 is greater than mg sine theta. Earlier kx1 balanced mg sine theta. Sorry, there's mg sine theta. Earlier kx1 balanced mg sine theta. So here kx plus x1. So this is larger than x1. So the resultant force acting on the trolley will be along the slope up. The resultant force is going to be kx plus x1 minus mg sine theta. This is the resultant force acting on it towards the equilibrium position. No. So when I solve it, it's going to be kx plus kx1 minus mg sine theta. But I know that kx1 is mg sine theta. Kx1 is mg sine theta. You can see that this kx1 is equal to, I got it first equation, kx1 is equal to mg sine theta. So it's going to be this kx1 and mg sine theta will get cancelled each other. Finally, we will have kx. But F is the resultant force, so that must be equal to ma. So ma is equal to kx. So A is going to be k over m into x. You can see x is the displacement from O. X is the displacement from O. Is it? O is the equilibrium position. The displacement downwards is x. So A is directly proportional to x because k and m both are constants. So A proportional to x. Also you can see the resultant force acting towards the equilibrium position. So according to F equal ma, acceleration will be towards the equilibrium position. X is away from the equilibrium position. See the diagram, x is away, downwards is x, but F equal ma, F is acting towards the equilibrium position, the resultant force. Therefore, the resultant force towards the equilibrium position means acceleration will be towards the equilibrium position. Therefore, A proportional to minus x. Therefore, it will be simple harmonic motion. Same way you can show when it is towards P2 somewhere here, the extension will decrease by x1, decrease by x. So I'll change that again. So same diagram I use it. So when it go to the P2, this is I derived when it is towards P1 from the equilibrium position and the trolley goes down, I derived it and show where A proportional to minus x. So if it is on the left side above O, towards P2 when the trolley is oscillating, I told between P1 and P2. So will it be a simple harmonic that side, or it must be, but we'll show that it's going to be x1 minus x. This condition is correct there also. When it is at equilibrium position, kx1 equal mg sine theta. And it's going to be x1 minus x because extension is going to decrease when the trolley moves upwards from O, this direction. Okay, kx1 minus x. So the resultant force, this is going to be smaller because kx1 balances mg sine theta. Now the extension is decreasing, so this tension is going to be smaller. So the resultant force is going to be towards the equilibrium position. Resultant force F is going to be, because this will be smaller than mg sine theta, the tension. So the resultant force will be towards O, that is going to be mg sine theta minus k x1 minus x. So solve it. mg sine theta minus kx1 plus kx. So here minus kx1. Kx1 is already mg sine theta. So here it's going to be mg sine theta. You can substitute for kx1. You substitute that mg sine theta and this mg sine theta will get cancelled. F equal kx. What's the direction of this f? This direction of the f is towards O because mg sine theta greater than this. So the resultant force is towards O. That is going to be MA. A is going to be towards O. So this shows A equal K over mx. So here also K and M are constants. So A is directly proportional to x. Also A is pointing towards the equilibrium position. X is from O upwards, but A is towards O. So it's going to be a simple harmonic motion. So when a trolley attached to a spring and when the trolley is kept on a slope where there is no friction, when you allow to oscillate, the oscillation will be simple harmonic here also. Okay, fourth example, a trolley is attached to two identical springs. Spring constant of each spring is k. It's not necessary to be identical, but for simplicity I took it identical. If there are any questions related to oscillations with two springs in your syllabus, it will be identical because otherwise k1, k2, two different spring constants, it will be slightly more work. Normally they won't ask that type of questions, I guess. Yeah, so for simplicity I took both springs are identical. When the trolley is at equilibrium position, each spring has the same amount of extension x1. So the extension of this spring is x1. This also has extension x1. Okay, so if I draw the free body force, this is the O equilibrium position. So if I draw the free body force diagram for the trolley when it is at equilibrium position, the weight and normal reaction balance each other. This side there will be tension T1 that is equal to kx1. This side also there will be tension T1, same thing, kx1. Okay, now the spring is pulled towards right. No reason taking towards right. If you want, you can take it towards left. Just for no reason, I am taking towards right through a distance, a small distance, and allowed to oscillate. But we take this way the questions. The trolley is pulled towards right such that the both springs are always under tension. That means, for example, if x1 is 5 centimeter, x1 is equal to 5 centimeter, you pull the trolley towards right, maximum 5, maybe 4 or 3, because then only, if you pull it to the right, this extension will decrease by, for example, if you pull it towards right by 4 centimeter, from O, the extension of the right side spring will become 1 centimeter. Already it extended by 5. Now you are pulling it to the right by 4 means it will reduce by 4. The extension of the right side spring will become 1. The extension of the left spring will become 5 plus 4, 9. If you pull it more than 5, then this spring will be compressed. Normally there are no such questions. So normally what appeared in the old past papers also I consider and do. So the trolley is pulled towards right and released. So you pull it towards right such that the amplitude of oscillation is less than x1. Okay, so always the springs both will be under tension. Okay, so it's pulled towards right and allowed to oscillate. So it's oscillating between the points P1 and P2. When it is on the right side, the extension is the displacement is x. So when the trolley is on the right side, I'll draw the diagram somewhere here. X, the trolley is here. The displacement from the equilibrium position, this equilibrium position is it. From the equilibrium position, the displacement is x. So if I draw the free body force diagram for this situation, if I draw the forces acting on it, weight and normal reaction will balance each other. So the right side, the tension now here, the T1, earlier it was kx1, now the T1 will become kx1 minus x, because the displacement from the equilibrium position is x. X is less than x1. Always we take that way, the amplitude of oscillation is less than the initial extension of the springs. So T1 equal kx1 minus x. Here the T2 is going to be, now it won't be the same T1, it's going to be T2 now. T2 is going to be x1 plus x. Okay, we know that this is greater than this because x1 minus x compared to that x1 plus x is larger. So the resultant force is going to be towards left. So when the trolley is on the right side, the resultant force will be towards left, means it will point towards O. So the resultant force is going to be k x1 plus x minus k x1 minus x. If you solve it, it will become kx1 minus kx1 plus kx minus kx1 plus kx. So kx1 get cancelled, it will become 2kx. Careful, 2k comes. In case if it is two springs with different spring constant k1, k2, then it will become k1 plus k2x. That's the only thing, there's nothing. k1 plus k2x will come. Since they are identical springs, it becomes 2kx. So the force is pointing towards O. Its resultant force is towards, when the trolley is on the right side of O, the resultant force is towards O. That means F equal ma, so it's going to be ma, or I can write ma, mass of the trolley is m, ma equal to kx, so A is going to be 2k over m into x, so the 2k comes. Otherwise, if there are two different springs, k1 plus k2 over m into x. We know that k is a constant, m is a constant, therefore A is directly proportional to x. Displacement, x is the displacement from the equilibrium position. So the acceleration is going to be directly proportional to displacement, and direction of acceleration is along the direction of resultant force, which is pointing towards O. Therefore, displacement is measured towards right, acceleration is pointing towards O, therefore A proportional to minus x. Therefore, it will be a simple harmonic motion. The same way you can prove by taking the trolley on the left side of O, the same results will come. This will become k x1 plus x, it will become x1 minus x. Same thing, we'll end up with the same result. So here also, the oscillation will become simple harmonic motion. Okay, the fifth example, a spring of which has spring constant k is hung on vertical plane, and when a mass, an object or small mass is attached to it, there will be a static extension. The spring will extend and come to rest. That is called static extension. So the static extension, let it be x1. So with the system, the spring mass system, when it is at rest, this position is going to be the equilibrium position. So the position at which the spring mass system comes to rest when it is not in oscillation will be the equilibrium position. So this is going to be the equilibrium position. Okay, so when it is at equilibrium position, the extension of the spring is x1. So when we think about the forces acting on the mass, there will be two forces acting on it. One is the weight acting vertically downward, and the tension, which is kx1, that is the tension. So since it is at equilibrium, kx1 will be equal to mg. Right. Now from this equilibrium position, we pull the mass further down and release. It will oscillate on a vertical plane. We imagine when during the oscillation at a particular instant, the displacement, I already told that displacement is always measured from the equilibrium position. So if the displacement is vertically downward, x, this is the mass. When the displacement is vertically downwards, x, the total extension of the spring will be x1 plus x. So that time, when I think about when we consider the forces acting on the mass, the forces will be downwards, mg, upwards, the tension, that's going to be T is equal to k x1 plus x. So when it is at the equilibrium position, mg is equal to kx1, but when it is below the equilibrium position, the tension will become greater than mg, so the resultant force acting on it will be towards the equilibrium position, that is upward direction. So at that moment, the resultant force, when it is at this position, when the displacement, which is x from the equilibrium position, at that moment the resultant force will be upward direction. So that is going to be F equal K x1 plus x, that is the tension, minus mg. Okay, so there kx1 plus kx minus mg. So it's going to be, instead of kx1 we can substitute mg, so that is going to be mg plus kx minus mg, that is, it will be kx. So the force will be equal to kx, Newton's second law if I use it, that is equal to ma. So the acceleration will be equal to k over m into x. This will be towards the equilibrium position. That's going to be towards the equilibrium position. So acceleration and displacement, x is the displacement when we consider, acceleration will be towards the equilibrium position because the resultant force is towards equilibrium position. Equilibrium position. So the acceleration will be towards the equilibrium position, which is directly proportional to displacement x. But x is measured from the equilibrium position, which is away, downward direction. You can see the x is downward direction, but acceleration is towards the equilibrium position. So they are going to be in opposite to each other. So there will be a minus sign in terms of vectors because this gives the numerical relationship. But acceleration is towards the equilibrium position, but x is downwards from the equilibrium position, which is downwards. So the direction of acceleration and direction of displacement, they are in opposite to each other. So A proportional to minus x. Therefore, K and M is constant. Therefore, I put a proportionality. That's the reason it's going to be a simple harmonic motion. It will oscillate in simple harmonic motion. Okay, same way, if the mass is above the equilibrium position, somewhere here if I consider what will happen, we don't need to do both sides, but I'm just doing it. In mathematics, in mechanics, for example, M3 we do it in a slightly different way, but in physics we don't go to that detailed analysis. But here we keep the mass somewhere here like this. So at that moment, the displacement is upward direction x. During that time, if I draw the free body force diagram, the forces acting on it will be weight is acting downward direction. The tension is going to be, when it is at the equilibrium position, the displacement is x1. Now it's reduced by x. So the extension is going to be kx1 minus x. Kx1 minus x is the extension of the spring. So the tension is going to be kx1 minus x. Okay, when I consider the resultant force during this position, when the mass is above the equilibrium position, here also we assume for simplicity the spring is not compressed at all, always the spring is under tension. So always this x will be smaller than x1, or the amplitude of the oscillation is going to be smaller than the static extension x1 if we take that way. And when the mass is above the equilibrium position, the tension is going to be kx1 minus x. Okay, so when it is at this position, when we consider the resultant force, it's going to be towards the equilibrium position, because we know that when it is at the equilibrium position, kx1 will balance mj. Now the tension has decreased, which becomes smaller than mg because the extension has become smaller than x1. So x1 minus x is smaller than x1. Therefore, the tension will become smaller than mg. So the resultant force will be towards the equilibrium position because mg is greater than tension when the mass is above the equilibrium position. So the resultant force F is equal to mg minus k x1 minus x. So if you solve it, mg minus k x1 plus kx. So here also instead of kx1 we can substitute mg. So kx1 we can substitute mg. So it becomes kx. So the resultant force is kx, which is towards the equilibrium position or downwards when the mass is above the equilibrium position. According to Newton's second law, it's going to be ma. So a is going to be k over m, a constant, into x, which is going to be towards the equilibrium position. So k over m is constant, therefore a proportional to x, but x is measured upward direction from the equilibrium position. This is upward direction. Acceleration is towards the equilibrium position, because resultant force is towards the equilibrium position. So the direction of acceleration, direction of extension are in opposite to each other. Therefore, A proportional to minus x, where k over m is constant. So A proportional to minus x means the system will oscillate or perform simple harmonic motion. Okay, so the sixth example about a child bouncing on a trampoline. So you know trampoline, it consists of an elastic material on top of it, like a elastic sheet on top of a membrane on top of it. So when a child stands on it, it will deform and the child will be at rest. So this position is going to be the equilibrium position. So now the child is bouncing up and down, such that it is always in contact with the elastic sheet or elastic that material. So when the child is at the lowest position, it's moving from the equilibrium position lowest position. The third diagram is showing that. So when the child is at the equilibrium position, so the sheet will exert a tension on the child upward direction. So in that situation, there are two forces acting on it. One is the weight of the child downwards, mg, and the elastic material, the sheet, will exert a tension push upward direction, that is T is going to be kx, where x is the x1, we can say that is the static extension from compared to the equilibrium position. This is going to be the static extension, this one, when the child is at equilibrium position. Okay, when the child goes further down during the oscillation below the equilibrium position, the extent is going to be more. It's measured from the equilibrium position. We can say the displacement is downwards, which is x. Displacement is downwards, x. So here the extension is going to be x plus x1, exactly same as vertically oscillating spring mass system, which is the fifth example what I explained. The same analysis we can do here also. So at this position, the child is below the equilibrium position. So there at this position, the forces acting on the child, there are two forces, weight is downwards. The tension is going to be now T is equal to K x1 plus x. So at the equilibrium position, Kx is equal to mg, so it balances each other. Now the tension has become greater than mg. So when the child is below the equilibrium position, the resultant force is going to be upward direction towards the equilibrium position. So there the resultant force F is going to be tension minus mg, that is K x1 plus x minus mg, that is kx1 plus kx minus mg. But we know that this at the equilibrium position, therefore kx1 is equal to mg. So instead of kx1, we can substitute mg. So mg minus mg will get cancelled. So it's going to be kx. That's going to be Newton's second law. According to that, F equal ma. F equal ma. So kx is equal to ma. A is equal to k over m into x. Okay, so when you consider this oscillation, the system, the child and the trampoline, the elastic material that forms the oscillator, oscillating system, so their acceleration is towards the equilibrium position, because resultant force is acting towards the equilibrium position when the child is below the equilibrium position. So the acceleration is going to be towards the equilibrium position, which is upward direction. But the displacement, which is measured from the equilibrium position, this is the equilibrium position. From the equilibrium position, the displacement is measured downward direction. So they are in opposite to each other. At the same time, k over m is constant. So acceleration is going to be directly proportional to displacement, but direction of acceleration is always towards the equilibrium position. You can see that here. Displacement is downward direction. They are in opposite direction to each other. Therefore, A proportional to minus x. When the child is below, I can show it is at equilibrium position. It performs simple harmonic motion. Sorry, not equilibrium position. When the child is below the equilibrium position, it performs simple harmonic motion. Same way, the child is above the equilibrium position. I'll draw the next position. The child is above the equilibrium position. So I'll use the same diagram. So I'll reduce the displacement like this. When the trampoline, the elastic material is above the equilibrium position. So it's like this way. So this is the equilibrium position. So the child is oscillating, and when the trampoline sheet with the trampoline material becomes above the equilibrium position, where the displacement is measured from the equilibrium position, it's going to be upward direction, is it? During this time also there are two forces acting on the child. One is the weight, other one, the extension is now decreased. Earlier the static extension is x1 when the child is at the equilibrium position. From that it started to move up and down or bounce up and down. Now the extension has become x1 minus x. At this position x1 minus x. Okay, we know that when the child is at the equilibrium position, kx1 balances mg. Now x1 minus x is smaller than x1, so the tension is going to be smaller than the mg. So the resultant force will be downward direction. So here the resultant force is towards the equilibrium position, which is downward direction, because tension is smaller than weight. So there the resultant force F is going to be mg minus t. So that is mg minus, instead of t we can say kx1 minus x. That's going to be mg minus kx1 plus kx. So kx1 is equal to mg when it is at the equilibrium position. I can substitute instead of kx1 mg. So mg and mg will get cancelled. It will become kx. F is equal to kx. The direction of the resultant force is downward direction, that is towards the equilibrium position when the child or when the elastic material is above the equilibrium position during the oscillation. So F equal ma. So F equal ma. F is towards the equilibrium position. So that is kx equal to ma. A is going to be downward direction towards the equilibrium position, k over m into x. Okay, you can see when the child is above the equilibrium position, acceleration is again pointing towards the equilibrium position. Acceleration is going to be downwards, means it's going to point towards the equilibrium position, downwards. The displacement is measured from the equilibrium position, which is upward direction. So they are among them in opposite direction to each other. Acceleration is pointing towards the equilibrium position. So A is going to be directly proportional, because km both are constant, kom is constant, so A proportional to minus x. So during the oscillation, whether the child is above the equilibrium position or below the equilibrium position, the acceleration will be always points towards the equilibrium position, and the direction of the acceleration will be opposite to the direction of displacement. Therefore that will perform simple harmonic motion. Acceleration is also proportional to displacement, so it's going to perform simple harmonic motion. So during the oscillation, if the child leaves the trampoline, so when the child, there was a question in the past paper, if the child leaves the trampoline during the oscillation, that means maybe the trampoline would have come to this position, something like this. Maybe the trampoline would have come to something like this horizontal position, or something like slightly upward direction. The child is thrown away from the trampoline, thrown away from the elastic material. Then will that system perform simple harmonic motion? No, because when the child is in air above the equilibrium position, the only force acting on the child is the weight mg. So the only force acting on the child is mg, means mg is equal to ma. So A is going to be g. That means the acceleration acting on the child is going to be constant, which is gravitational acceleration. It does not proportional to the displacement from the equilibrium. So this is the equilibrium position. The displacement of the child from the equilibrium position may be x, but acceleration is constant, that is not proportional to displacement. Therefore it won't be a simple harmonic motion. So when the child leaves the trampoline and when the child moves freely away from the trampoline, then the system, which we include child and the trampoline, will not perform simple harmonic motion at that moment, because the acceleration of the child becomes constant. It won't be directly proportional to displacement. Okay, the seventh example is about oscillation of a weighted test tube or small tube inside a liquid such as water. So initially the tube is at equilibrium. When it is at equilibrium, the length L of the tube is inside the liquid or water, we'll say it. So at that situation, if you think, consider the forces acting on the system, that is forces acting on the weighted test tube, downward direction weight, upward direction upthrust. I'll draw the whole system, the weighted test tube as a small circle, easy for that to draw. So the forces acting on the weighted test tube, downwards weight mg at the equilibrium position, and upwards the upthrust, U, upthrust, what you learned in unit 1. Upthrust is equal to weight of the displaced fluid. So the length which is inside water is capital L. So the upthrust is going to be weight of the displaced fluid, means or weight of the displaced liquid. Water will take it as that. We need to find the upthrust. Volume, we need to consider the volume of the liquid displaced is going to be cross-sectional area. If I say capital A, the cross-sectional area, the length into L, that is the volume, into density of the liquid rho into G, this is the upthrust. So at the equilibrium position, the upthrust is equal to weight. So U is equal to mg at the equilibrium position. So from the equilibrium position, imagine you push the test tube little bit down and allow it. So the test tube will oscillate in vertical, on a vertical plane. So when the displacement, this is the equilibrium position, the blue color line what I drew. So when the test tube is at rest, so you push it down from the equilibrium position and allow it to oscillate. So when the displacement is downwards from the equilibrium position, the displacement is x. During that situation, the upthrust is going to be u1, that is going to be the total length inside. So this is L already, L was inside. So this is anyway again L, the equilibrium position, which was L below the level of the upper surface of the liquid. So now the total upthrust is going to be, U1 is going to be the U1 now, or you can say even U, whatever it is. Volume of the displaced liquid is cross-sectional area into length inside the liquid is L plus X into rho G. So the two forces acting on it, one is the weight downwards and the upthrust. Now since the tube has moved inside, the amount of the water displaced or the volume of the liquid displaced is going to be more. So upthrust U1 is going to be greater than U. So when I consider the resultant force acting on the system, the test tube, it's going to be upward direction, because the resultant force is going to be upwards because the upthrust is more now compared to when the tube was at the equilibrium position. So the resultant force is going to be upward direction, that is F is equal to U1 minus mg. So U1 means A L plus X rho G minus mg. So that is, if you multiply inside, A L rho G plus AX rho G minus mg. AX rho G minus mg. So when we consider this AL rho G and mg are same, so AL rho G, I can replace this AL rho G by mg. So mg plus A rho Gx, I rearrange it, A rho Gx minus mg. So mg will get cancelled, it's going to be A rho Gx, the resultant force that is acting upward direction towards the equilibrium position. So upon Newton's second law, this is going to be ma. So acceleration will be along the direction of resultant force. You learned that in unit 1. So acceleration also will be towards the equilibrium position, that is upward direction. So if I make the A subject, A is going to be A rho G over m into x, which is upward direction when the tube is below, or the weighted tube is below the equilibrium position. So the acceleration is upwards, means it's pointing towards the equilibrium position, but x is the displacement we measured from the equilibrium position. So displacement is downward direction, acceleration is upward direction. This all constant, cross-sectional area constant, density of the liquid constant, G constant, total mass is constant. So these all are going to be constant. So A proportional to minus x, because they are in opposite direction. So when the tube is below the equilibrium position, what will happen? A proportional to minus x, A acting towards the equilibrium position, Therefore, it will perform simple harmonic motion when the test tube is below the equilibrium position. Same way, when the tube goes above the equilibrium position, something like this if we consider, the tube goes above. So there we can draw a diagram again like this. It has gone up above the equilibrium position. This is a weighted tube. So this is the equilibrium position. So the displacement is upward direction. So the length of the test tube inside the liquid is now it's going to be L minus, this whole thing is L. So it has gone up above the equilibrium position. So you know that from the surface of the liquid to equilibrium position is the L, capital L. So the same thing, this is the capital L from the surface of the liquid. So from the surface of the liquid to this equilibrium position. So the equilibrium position is drawn with blue color line. This is L. From here to here is L. From this position to this position is L. Is it? We take that as L. Now the length actually inside the liquid is going to be this much. That is going to be L minus X. So that is going to be L minus X is the length of the tube inside the liquid. So L minus X is smaller than L. So what will happen? The upthrust is going to be now L minus X. Now we can say the upthrust is L minus X. So when it is at the equilibrium position, the upthrust is equal to weight. But now the upthrust becomes smaller than the upthrust when it was in the equilibrium positions. Therefore, the resultant force is going to be upward direction. The resultant force is going to be downward direction because the upthrust has become smaller now. So when we consider the resultant force, it's going to be mg minus u1 when the tube is above the equilibrium position. So mg minus u1 when the tube is above the equilibrium position. So that is going to be mg minus u1 is a L minus x rho g. So that's going to be mg minus a L rho g minus a rho g x. A rho g x. Okay, so instead of a L rho g, I can substitute mg. So this mg and this mg will get cancelled. Mg minus mg minus a plus minus into minus plus a rho g x. Okay, so that is going to be F. The resultant force is going to be a rho g x, which is the direction is downward direction because mg greater than u1. So the resultant force when the test tube is above the equilibrium position, that will be downward direction. So that's going to be ma. So the acceleration will be downward direction. So a is going to be a rho g over m into x. Acceleration is downward direction. Acceleration will be downward direction, but the x displacement is measured upward direction. So they are in opposite direction to each other. Also, you can say acceleration is directly proportional to displacement. Acceleration is pointing towards the equilibrium position. When the weighted test tube is above the equilibrium position, it's pointing towards the equilibrium position. So a proportional to minus x. So it will perform simple harmonic motion. So I separately did below the equilibrium position, above the equilibrium position, make you to understand. So whatever the direction it stays, whatever the direction it is in motion, whatever it is, the acceleration is towards the equilibrium position and proportional to displacement such that the displacement and acceleration have opposite direction among them. So it will perform simple harmonic motion. Okay, so I summarized all the examples I did. The first example I didn't write because I told that when a small ball bearing oscillates on two inclined planes like this, which makes theta theta, that won't behave or that won't show simple harmonic motion. So I didn't draw that. Other than that, all other 6 examples I drew it. So in all these examples we came across, we gave a conclusion A proportional to minus x. A proportional to minus x means K over M is constant, K over M is constant, 2K over M, because here 2K comes, there are 2 springs, identical springs attached on either side of the trolley. So here K over M constant, so here trampoline also K over M constant, A rho G over M constant. So everywhere there is a constant there. So generally I can conclude in simple harmonic motion, the acceleration is directly proportional to its displacement with minus sign indicates they are in opposite direction to each other. So A is equal to minus Cx, I can say. There's a constant C. The C could be different for different examples. For example, here the constant C is 2k over m. But in all these others, k over m, k over m, k over m. But here the constant is A rho G over m when weighted test tube oscillates in liquid. Anyway, whatever, the constant could be different for different types of oscillators, but there is a constant C. Okay, so what is the meaning of this constant? What does it mean? What's the physical meaning of this constant? We need to know that. Okay, so to identify actually what this constant C represents in simple harmonic motion, we know that simple harmonic motion occurs or happens in one dimension, either up and down. You can see all these things, it's happening left and right, one dimension. This is also one dimension on a slope, either along the slope or upward in a slope. This is one dimension left or right, this one dimension up or down, one dimension up or down, this also one dimension up or down. So the oscillation, simple harmonic motion happens in one dimensional motion, either up or down or left or right, like that. Okay, so what is the meaning, the physical meaning of C? We want to find it. Okay, so actually to relate or get a physical meaning, we need to relate the simple harmonic motion. Could be related actually. Simple harmonic motion could be mathematically related to circular motion, even when simple harmonic motion is not happening in circular path. When we consider the simple harmonic motion, there is no circular motion actually. It's happening in one dimension. Circular motion happens in two dimensions. But even there is no two-dimensional motion in simple harmonic motion that happens in one dimension. Even that way it happens. Mathematically we can relate the simple harmonic motion to circular motion. From that we can identify the physical meaning, actual meaning of C. What could be the effect of C? For example, in this particular oscillation, what will happen if the constant increases by increasing the spring constant of the spring, or by reducing the mass attached? If I increase the constant, what will be the outcome? We can find it. Same way, here also by increasing the density of the liquid, we can increase the constant C related to this oscillation. So what could be the outcome of that? We can identify. So to identify that, we should know the meaning of C. Okay, that could be explained by using a circular motion mathematically. Okay, so we'll consider a particle is moving on a circular path of radius capital A. Center is O, moving on a circular path at constant angular speed omega. For simplicity, no reason, I can take initially anywhere, but for simple thing, I took it initially. The particle is along the diameter in horizontal position at this position initially when t equals 0. Later, at time t equal t, the particle has come to this position. So when we draw a projector means a vertical line from the particle to the diameter. I consider the horizontal diameter. We can draw to any diameter, but simple thing, we consider a horizontal diameter. So if you draw a projector from the particle to the diameter, the base of the projector touches the diameter, which is in horizontal position at point N. So the distance of the N is the projector drawn from the particle to the diameter. The distance of the N from O is x, which is directed towards right. So in this right angle triangle, we know that x is going to be a cos theta. But the particle is rotating, moving at constant angular speed omega. Therefore, we can say omega equal to theta over t. From the theta is equal to omega t. So x is going to be a cos omega t. Okay. So x is the position of the distance of the projector from O. You can see that, imagine that when the particle moves from this position, I'll name this position as initial position P, this as Q. When the particle moves from P in anti-clockwise direction. The projector, when the particle is at P, projector N will be at P. When the particle moves this way, the projector will move towards O. When the particle is at exactly at this position, exactly above O, the projector N will be at O. When the particle moves further towards left, the N will move from O to Q. So initially the projector was at this position. Here if I say this is O, the projector will move from P to O. Then when the particle moves to O, it will move from here to here to Q. When the particle comes to this position, what will happen if I draw a projector? Again the projector will move from Q to O, then again from O to P. So that means simply I can say when the particle completes one full circular path, the projector will drawn to horizontal diameter will move from P to Q and again from Q to P. So when the particle completes one full circular path, the projector will complete one full oscillation about O. So the time taken for the circular motion and the time taken for the projector to complete one full oscillation will be exactly the same. Okay, so that's a comparison we are going to do. Right, so we know that x equal a cos omega t. Okay, what could be the, I told that the particle is moving at constant angular speed omega. So when the particle moves at constant angular speed, what could be the speed of the projector n when we measured? That's going to be differentiation. Anyway, not in the physics, but just for your information, that's for your knowledge I'm doing it. When you differentiate x with respect to time, that is speed is going to be dx over dt. When you differentiate this, it will become minus a omega sine omega t. When you differentiate cos, it will become minus sine. You add a different, when you differentiate omega, it will become omega. So minus a omega sine omega t. That's going to be the speed. Anyway, don't worry. So that is the speed of the projector n. When we measure, when you differentiate again, we'll get acceleration of the n when the particle moves on circular path around it. So the acceleration is going to be dv over dt or d2x over dt to dv over dt. So when you differentiate the velocity again with respect to time, you are going to get minus a omega. Again this omega comes out, so a omega into omega, a omega squared, sine will become cos omega t. So that's going to be minus omega squared a cos omega t. So a cos omega t is going to be x. So that's going to be minus omega squared x. That is the acceleration. See, now you can see that the projector n has an acceleration that also have the same format what we got earlier in all examples. A is equal to a constant minus c into x format. You can compare the both. When we consider the acceleration of the projector n, that a is equal to minus omega squared x. X is the displacement we can call, which is measured always from center O when it oscillates in circular path. It's going to oscillate on the diameter. So we can consider this as the equilibrium position because it's oscillating on either side. So mathematically, when you compare, both are similar equation. X is measured from the equilibrium position. So c is the constant. I came across in all examples there's a constant c. That c gives angular speed omega squared. So you might ask how angular speed is related to one-dimensional oscillation. Yes, actually angular speed is not related to one-dimensional. Actually the simple harmonic motion is not performed in two dimensions. It's actually moving on one line, but mathematically we can relate the constant what we observed in the previous examples, constant c, as square of the angular speed. Now we will forget about c, that we can replace by omega squared. So in all those examples what we came across, for all type of simple harmonic motions, the constant what I told is going to be omega squared. So a is going to be minus omega squared x. In circular motion, I told that when it completes one full circular path, the projector will complete one full oscillation. So omega, we know that for circular motion omega equal 2 pi over t or omega equal 2 pi f, we know that. So The time period of the circular motion, what we imagine here, and the oscillation have the same exactly time period. So when we consider all the simple harmonic motions, the 6 examples what I consider, in all those 6 examples, omega squared indicates angular speed, but angular speed won't be something irrelevant for the simple harmonic motion. It looks like that, but we can say it's of omega, that is going to be 2 pi over t minus 2 pi over t. Now it has meaning 2 pi over t all in square x. That means we can say acceleration of a simple harmonic motion is equal to minus 4 pi squared over square of the time period of the oscillation. Simple harmonic motion has a constant time period into x. We can say that way. Then it has meaning where t is time period of the simple harmonic motion. How I got this t? By comparing the circular motion and the simple harmonic motion. Mathematically we got it. There's another way also there, but I'll do it at the end of this lesson. Without comparing circular motion and simple harmonic motion also, we can get the actual meaning of C, but little bit of differential equations, like a second order differential equation, we have to use it. But anyway, like d2x over dt2, that is the acceleration, is equal to dt2 is equal to minus that is equal to minus cx. From this we can show that, but anyway I don't want to go to in that detailed mathematics. If you want I can do it at the end, we'll see. If I want I can do that finally at the end of this lesson. But anyway, you know that acceleration is equal to minus 4 pi squared over t squared, we can say. Then there is the meaning. T squared is the time period of the simple harmonic motion, the time taken to complete one full oscillation, t squared into x. Or you can say A is equal to minus 2 pi f all in squared x. Then there is meaning where the constant is 2 pi times f. Okay, f is the frequency of the simple harmonic motion. Okay, so in this example, we took the radius of the circular path is capital A. That is actually the amplitude of the simple harmonic motion, amplitude of the simple harmonic motion. So A, I took it as the radius of the circular path. That is actually the amplitude of the simple harmonic motion. Also, here we took the oscillation. Initially, the particle was at P and it's moving in anti-clockwise direction. So we got x equal A cos omega t. That means if the particle is moving initially from the positive displacement maximum position, initially if the particle is at P, that means when I consider the equivalent or the relevant simple harmonic motion, when the particle is at P in circular motion, in simple harmonic motion, it has the maximum displacement which is equal to amplitude A. So initially when t equals 0, when the particle is at the maximum displacement position in simple harmonic motion, initially if the particle is at the maximum displacement position, that means at the extreme position, and then later at a point here, means somewhere here when the particle comes, the time taken t for motion from P to this position, the time taken is t, means the displacement from the equilibrium position x is given by x equal A cos omega t. You must know that the displacement is given by x equal A cos omega t. That means initially the particle is at the maximum displacement position, that is extreme position. Then it's moving towards the equilibrium position. So it's moving in circular path anti-clockwise direction. So here the equivalent simple harmonic motion is moving towards the equilibrium position. At time t, the displacement is x, means that is given by x equal A cos omega t when initially the particle is at the extreme position. But other way also we can consider the particle was initially here. We'll consider the particle was initially at the equilibrium position, means the particle is initially at this position. Then it's moving from O to P, means it's moving in this direction. So initially that is t equals 0 if the particle is here, not here. Initially the particle is here and rotating in this direction. This direction is moving at constant angular speed omega. So in that situation, we take the angle this as alpha if I consider. Later at time t equal t, it rotated from this position through angle alpha, means the theta is going to be 90 minus alpha, or if I consider this as alpha, then this as theta, so the alpha is going to be 90 minus theta. So in that situation, the displacement on the same horizontal diameter, that's going to be x equal a cos theta. Instead of cos theta, I should say x equal a cos 90 minus theta. Cos 90 minus theta is going to be sin theta. X equal a sin theta. You know, cos 90 minus theta equal sin theta. So that means if the particle was initially at the equilibrium position at O, and late at time t it has a displacement from the equilibrium position, which is x, and it's moving towards the extreme position, then late at time t the displacement is given by x equal a sin omega t. Instead of theta we can put omega t. X equal a sin omega t. So that also you must know. You should know where to use which equation. That means initially if the particle was at the extreme position and late at time t, the displacement is given by x equal a cos omega t. But if the particle initially at the equilibrium position, then late at time t, displacement is given by x equal a sin omega t. So you should know where to use which equation. Remember that initially if it is at the equilibrium position, late at time t, x equal a sin omega t. Initially it is at the extreme position, late at time t, x equal a cos omega t. So in all these examples, again if I consider the example which I did second, first one was not simple harmonic motion when a marble or like a ball bearing oscillates on two inclined surfaces. It won't perform simple harmonic motion. That's the first example I discussed. So I'm not going to consider that anymore. The second example what I showed in the previous examples, that I put it as first, whereas trolley oscillate on horizontal line. Horizontal plane A is equal to minus k over mx, we got it. So that means that's omega squared x. Is it? Omega squared x. Because it's a constant, k over m is constant. I already showed by comparing the simple harmonic motion and the circular motion, the constant is omega squared. So that means omega squared is equal to k over m. That is omega is going to be square root of k over m. That is omega equal 2 pi over t, from the t equal 2 pi square root of m over k. From this we can find the time period of oscillation if I know the spring constant and mass of the trolley. Same way when it oscillates on a slope like this, I derived it, but I am not going to do again. There are also, when a trolley oscillates on a slope something like this, there are also the equation we got exactly the same. So for that also the time period will be t equal 2 pi square root of m over k. Okay, so then when we consider trolley which consists of the next example, I put two but not exactly the same earlier two. A trolley which is attached to two springs with same identical spring constant. There I showed that A equal to minus 2k over m into x. So this is equal minus omega squared x, that is omega squared equal 2k over m. If the springs constants are different, then it will become k1 plus k2, but rarely that type of questions comes. Identical springs is a simple thing, that's the way the questions come normally. So omega squared equal 2k over m. So that is omega is going to be square root of 2k over m. Careful. Not k over m. There are two springs, so that's the reason 2k over m. If they are different springs with different spring constants k1, k2, then it will become it will become k1 plus k2. In that situation, you can try the derivation. Omega squared will become k1 plus k2 over m. That's the way you will get it. Okay, but here identical springs, so 2k over m. K1, k2 both are same, so k plus k, 2k we are getting. So omega equal 2 pi over t. So t is going to be 2 pi square root of m over 2k. But if the spring constants are different, there you will get omega is going to be, in that example, omega is going to be square root of k1 plus k2 over m, that is 2 pi over t. So t is going to be 2 pi square root of m over k1 plus k2, you will get it, if the spring constants are different. For the trampoline also, the example which related to trampoline, there also the equation was the same as earlier, that is we got a equal minus k over m x. So there also the time period is exactly same as this one. I don't need to work it out again because you can compare the same format we are getting for the trampoline. See the thing again if you want, same pattern we are getting. So the time period will be exactly the same for the trampoline also. Only this is the different. When there are two springs, remember the spring constants different, same spring constants for the both springs. Okay, next is for the oscillation of the weighted test tube when it oscillates in liquid. We obtained the equation A equal minus A rho G over M into X. Is it? That's already obtained earlier. So here it could be compared as A equal minus omega squared x. So omega squared is equal to A rho G over M. That is omega is equal to square root of A rho G over M. That is equal to 2 pi over T. So the time period T is going to be 2 pi square root of M over A rho G. Okay, so here I asked that what will happen to the oscillation when the density of the water is increased. When the density of the water increased, the time period is going to be smaller. Time period is smaller means we know T is equal to 1 over F. The frequency will become higher when the density increases. Say for example, same weighted test tube could be oscillated in pure water and salt water. Salt water higher density, or pure water and oil. Pure oil is lower density. Whatever it is, when we think about two different media, the same weighted test tube is oscillated separately during different times. So the rho could be different. When higher the rho, lower the T. Lower the T means higher the frequency, the rate of oscillation will increase. So after we compare the circular motion, simple harmonic motion, now we know the meaning of C, what could be the outcome of oscillation. Even when we consider this equation, what I just now got, T equal to 2 pi square root of M over K for a trolley as attached to a spring. When the mass of the trolley increases, time period will decrease, frequency of oscillation will increase. Like that, we are now able to analyze the outcome of oscillation when one of the constants varies. Or whenever rather than saying when of the constants varies, whenever one of the constant is changed by the experimenter, what could be the outcome? We know that now by using this A equal minus omega squared x. Okay, next thing is about simple pendulum. Simple pendulum means an inextensible string. One end is attached to a fixed point and the other end is attached to a small bob, and it will oscillate about the fixed point from where the string is attached. Say when the simple pendulum is at rest, this is going to be the equilibrium position. The equilibrium position will be taken as the lowest position. So it will oscillate something like this path on a segment of a circular path. When it is at this position, when we consider the position here, the displacement of the simple pendulum will be measured from the equilibrium position. So this is the equilibrium position. So the displacement is going to be this one. This is the displacement. So at this instant, the string makes an angle theta from its equilibrium position. So this is the equilibrium position. Okay, so we are going to check whether the simple pendulum follows the condition for the simple harmonic motion. It oscillates. I told that already at the start of this lesson. All the oscillations are not simple harmonic. We'll see whether this type of oscillation, a simple pendulum, does it show the is the oscillation of simple pendulum is a simple harmonic motion? We are going to check that. Okay, for that we need to consider smaller angles, because otherwise it's difficult to show that. For example, when it is at this position, this is the equilibrium position O. When it has this position, we can say the position P, the weight is acting vertically down mg. Mg is the weight acting downwards. It makes an angle theta with vertical, means this angle is going to be theta. So this also will be theta here. This side, this also will be theta here. Okay, if I want to resolve the weight, so there are two forces acting on the bob. One is weight, the other one is tension. Right. If I want to get a component of these forces towards the equilibrium position, the simplicity, the condition what we need to consider here is when we take smaller angle theta, what will happen? The component, say when the angle become theta, you know, if I consider this triangle, if I name it this point O, this is this point is named P. If I say this name point Q, when I consider the triangle OQP, this length is L is the length of the string, the same string, so this also L, so this OQM is an isosceles triangle, so these two angles will be the same. If I take this angle alpha, this also will be alpha, is it? In this triangle OQP, if this is alpha, this is also alpha, because these two sides are same. So we know that theta plus 2 alpha is equal to 180. If the theta is very small, almost something like 2 degree, 3 degrees, something like that, very small angle, then what will happen? Theta very small means I can compare to 180, that is negligible. So I can say approximately 2 alpha approximately equal to 180. So alpha is going to be 90 degree. That means when the theta becomes very small, something like 3 degree, 4 degrees, something like that, this angle will become almost 90 degree. So that means the displacement what I consider from the equilibrium position will be perpendicular to the tension. The displacement will become perpendicular to the tension. That's I want, right? So when the theta becomes very small, alpha I showed it will become almost 90, not exactly 90, almost equal to 90. That means the displacement what I showed by x will become perpendicular to the string, that means perpendicular to the tension. So in that situation, this is 90 degrees. So I'll draw a line something like this way. Again I'll draw it, this triangle here. This is a line. So this is almost 90 degree. So if this is 90 degree, what will happen? This is 90 degree. So this is theta. This is going to be 90 minus theta. See this angle will become 90 minus theta. That means the weight will make an angle 90 minus theta with the displacement. So the tension is going to be perpendicular to the displacement. So in that situation, if I draw the free body force diagram, the weight is vertically acting downwards, mg. The displacement x makes an angle 90 minus theta. This line, the blue color line what I drew here, that will make an angle 90 minus theta with mg. And the tension will be perpendicular to the displacement. So this is 90 degree. So tension won't have any component along the line that shows the displacement. Okay. So the only force acting on the bob towards the equilibrium position is going to be mg cos 90 minus theta. So the resultant force acting on it towards the equilibrium position, that is called restoring force. Earlier also we came across restoring force in all my examples in earlier. So the resultant force towards the equilibrium position is going to be mg cos 90 minus theta is going to be ma. That is mg sin theta is equal to ma. That is A is going to be g sin theta. This is true when theta is very small. Here also I can write when theta is small angle or very small angle. In that condition only I got it alpha 90 and the displacement perpendicular to the tension. I got all those conditions when theta is very small. So A is going to be G sin theta, and you know this force is acting towards the equilibrium position. So the acceleration is towards the equilibrium position. Okay, so here sin theta comes. How can I eliminate the sin theta? We know that when the angle is very small, when theta is very small, sin theta is approximately equal to theta in radians. We know that. So I can say this is A is equal to G theta. Okay, now we'll consider another approximation. Now we know that in this isosceles triangle, the length x will be almost equal, the displacement x will be almost equal to the length of the segment drawn part of a circle. The length of the segment what we draw by black color line dot 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 is almost equal to the displacement x because theta is very small. So in that situation we know the length of this arc is given by the length of the arc. If I say s, that is equal to the length of the arc s is equal to r theta. We know that r theta, here r is L theta, but L theta is going to be almost equal to, that is s, which is equal to displacement for small angles, so that's going to be x. So theta is going to be x over L when theta is very small. So this I can write A is equal to G. Instead of theta I can write x over L. That's going to be G over L into x, that is A. We know that A is already pointing towards the equilibrium position. The resultant force is acting towards the equilibrium position along this line, the displacement drawn the same line. So A is towards the equilibrium position. X is measured from the equilibrium position. They are in opposite direction to each other. And we know that G and L both are constants. So since G and L both are constants, this is going to be A proportional to minus x. Again I'll tell here G over L is constant. A is pointing towards the equilibrium position O. X is measured from the equilibrium position. So they are in opposite direction to each other. Also, since G over L is constant, A is directly proportional to minus x, where A is pointing towards the equilibrium position. So simple harmonic motion, simple pendulum also performs simple harmonic motion, but the important conclusion is when the angle of oscillation is very small, within 5 degrees or something like that, such that where the length of the segment of the circle, the dot dot line, and the displacement becomes equal. In that situation, sin theta equal to theta. So when it has a small angle of oscillation, simple pendulum performs simple harmonic motion. So G over L. So we can write again. So I'll write this. From this I can write everything together again. So A proportional to S, that is A is equal to G over L into X. So they are in opposite direction. So A equal opposite direction. So minus X, if I say minus G over L X, that is A equal minus omega squared X. Omega squared equal G over L. Omega equals square root of G over L, that is 2 pi over T. So T equal 2 pi square root of L over G. This is a standard equation given in the data sheet also. This is a time period of simple harmonic, simple pendulum. Okay. So the condition, very important, theta must be very small. So we can say when theta is very small, okay, so if I summarize up to what we learned, the first equation what we learned is A equal minus omega squared x, or we can say A proportional to minus x. The constant is omega squared. What's the physical meaning of omega? We know that omega equal, we did already, 2 pi f. So omega indicates how fast the oscillation happens in a normal way. If I say very simple way, omega indicates the physical meaning. It shows how fast the oscillation could happen. That means for an oscillator with higher omega, the oscillation will happen at higher rate per second. We can say simple way, because omega equal 2 pi f. When f increases, omega will increase. So higher the omega, that means the rate of oscillation will be higher. That's the physical meaning of the constant, what relates A proportional to minus x. Okay, second we got an equation for displacement, x equal A cos omega t. We must know where to use this equation. The other one is x equal A sin omega t. So what are the conditions to use these two equations? X equal A cos omega t means if the oscillator initially at the extreme position means position where the displacement is maximum initially when t equals 0, if it is at the extreme position, and later at time t its displacement is given by x equal A cos omega t. We'll do questions later. The second, x equal A sin omega t. What's the meaning of it? Initially when t equals 0, if the oscillator is at the equilibrium position, then later at time t, if I want to define the displacement, it's given by x equal A sin omega t. Okay, then we should know the equation for the velocities also. If x equal A cos omega t, then the velocity is given by v equal, if you differentiate, but equation is given in the data sheet. So remember that, or you can see the data sheet. If x equal A cos omega t, the velocity is given by minus A omega sin omega t if x equal A cos omega t. So that means if the displacement obeys this format, then the velocity of the oscillator at a time t is given by v equal minus A omega sin omega t. Same way, if the displacement obeys this equation, then the velocity is given by A omega cos omega t if x equal A sin omega t. Remember this equation. So you can see all the displacement with time, velocity with time, they all follow sine shaped graphs, sinusoidal graphs. Yeah. Okay, so we know that A equal minus omega squared x. How the acceleration varies with time? So that also we can relate A equal minus omega squared. Instead of x, you can substitute A sin omega t, or A equal minus omega squared. I'll write the cos first. Everywhere I'm writing cos first, so I'll write A cos omega t, or minus omega squared A sin omega t. So that means the graphs of, I'll show that graph, the graphs of displacement against time, that is a sinusoidal graph. Cosine or sine, similar shape, the phase difference is 90. The same shape, you know the shape of the graph, sine or cos. Same way, velocity against time, that also the same pattern, sine or cos graph. Acceleration against time, that also sine or cos shape of graph. All same similar shape, that is sine or cos shape of graph. Okay, so next you must know what could be the maximum velocity. Anyway, I don't want to show in mathematical format, but better remember what I am going to give as conclusion. So these are the 4 points. Then the 5th point, I'll write it here. The maximum velocity happens. Where does it occur? Maximum velocity occurs at the equilibrium position, which is given by V maximum equal A omega. Remember that maximum speed, the speed is changing with time, sine shape. Maximum speed or maximum velocity, magnitude of the maximum velocity is A omega at the equilibrium position. Remember that, you must know that. Then maximum acceleration, the maximum, okay, before that, minimum speed, what is the minimum speed? V minimum is equal to 0. because it's sine shape, there will be 0 comes, is it? So minimum speed, that is 0, where it happens at the extreme positions, at the extreme position, left and right or up and down the extreme position. Okay, then seventh equation, acceleration maximum, where it happens, that's you know that A equal omega squared x. Omega is constant. When x becomes amplitude capital A, negative sign we don't need. Numerically we are analyzing. When x becomes capital A max equal omega squared A, omega squared A, that happens at the extreme positions, left and right or up and down. The extreme position where the amplitude happens at the extreme positions. Then the eighth one, A minimum, where that happens, minimum acceleration is 0 at the 0 at the equilibrium position. So I concluded the whole thing what we learned so far. This equation is applicable. All these common for all the type of oscillation we came across now. Oscillation of a trolley or mass horizontal plane, oscillation of a mass on a slope with a spring, oscillation of spring mass system in vertical plane, oscillation of trolley with two springs, oscillation of trampoline, oscillation of weighted test tube inside liquid, oscillation of simple pendulum. For everything we can use all these equations. All these equations applicable for generally for all type of simple harmonic motions. Better remember these things. Where the maximum occurs, what is the maximum, where the minimum occurs, what is the minimum. Better remember that also. Okay, so based on this, we'll do few numerical calculations now. Okay, so this is the first question. We need to find the angular speed of this oscillation. So it says that a pendulum operates, a grandfather clock is released from its maximum displacement position. That means initially when t equals 0, if I consider t equals 0, the displacement is maximum. That is, the displacement is maximum means this is 10 centimeters. Okay, it swings completely through one cycle every 2 seconds, means the time period is given, t is equal to 2 seconds. So first part they have to find the angular speed. So answer for the first part, omega equal 2 pi over t, that is 2 pi over 2, that is pi radians. So pi means the time period is equal to 3.14 radian per second. That's the answer for first part. Okay, the second part of the same question, find the distance of the bob, that is displacement, distance of the bob from the reference point is given from the equilibrium position at 8.2 seconds. So initially it was released from the extreme position. So when t equals 0, the bob was released such that the displacement, these are small oscillations, so I already told that, initially the displacement was 10 centimeter. So if you pull an oscillator from the equilibrium position through a particular distance and released, that initial distance from where you release will become amplitude of the oscillation. Again I am telling, if an oscillator is moved through an equilibrium position, a particular distance through a particular distance from the equilibrium position and released, the initial distance from what you push the oscillator from the equilibrium position, that distance will become amplitude during the oscillation. So in this example, the pendulum bob is pulled through a distance of 10 centimeter and release, means 10 centimeter will become amplitude during the oscillation. So the amplitude is 10 centimeter. So initially it was released from the extreme position. I already gave two equations to find the displacement. One is x equal a cos omega t. Then the second one I gave x equal a sin omega t. I already told that this equation we use if the oscillator is initially at the extreme position. Then to find the displacement later at a particular time, we use x equal a cos omega t. Initially, if the oscillator is at the equilibrium position, and if you want to find the displacement later at time t, we use x equal a sin omega t. So here, the oscillator, the simple pendulum, is released from the extreme position, means initially we had used x equal a cos omega t. So find the distance of the bob from the equilibrium position at 8.2 seconds. So that means at 8.2 seconds, what will be its displacement? That's the question. So x equal a, the amplitude is 10 centimeter into cos omega 2 pi over t into t. Okay, so we'll substitute 10 cos omega. We already found it in the previous part, or we know the t time period 2 seconds, so 2 pi over 2 into time t is equal to 8.2. Solve it. When you solve, your calculator must be in radian mode because we are using in radians. Cos 2 pi is a radian. So solve this, you will get 8.2 centimeter. Sorry, that's 8.09 centimeter. That's answer, not 8.2, 8.09 centimeter. Okay, so the second question, a science museum has a giant demonstration tuning fork, something like this tuning fork, you know that. These are the prongs are vibrating in simple harmonic motion, and the period of the vibration is 1.2 seconds. So period capital T is 1.2 seconds and starts vibrating from amplitude of 80 centimeters. So that means initially it has an amplitude, that is it is at the extreme position. Initially when t equals 0, it has a maximum displacement which is 80 centimeter. Calculate the displacement at 5 seconds. So initially it is at the maximum displacement position which is 80 centimeter. We need to find the displacement at 5 seconds from that extreme position. Initially it was at extreme position. So the equation that we need to find use here is x equal a cos omega t. We can use x equal a sin omega t if the oscillator was initially at the equilibrium position. So here it was at the extreme position initially. Okay, so amplitude we know that 80 centimeter. We can do it in a meter or centimeter. So we'll do it in centimeter. So 80 into cos. We know that omega equal 2 pi over t. So cos 2 pi over time period is given 1.2 into 5. You should keep your calculator in radian mode. Solve this, you will get 40 centimeter, or you can say 0.4 meter. That is the displacement at 5 seconds. Second part, we need to find the speed in 5 seconds. I already gave the equation, all I gave it as a summary. So if the displacement is given by x equal a cos omega t, then speed is given by x equal a omega sin omega t. There will be a minus sign, I don't need it. When you differentiate this becomes minus, that we don't need to consider. We are dealing with speed, only the magnitude. So a omega sin omega t. So amplitude a is 80 centimeter. We can say 0.8 omega 2 pi over t 1.2 into sin 2 pi over 1.2 into at 5 seconds 5. This much of meter per second. Solve it, you will get 3.63 meter per second. That will be the speed of this prong at 5 seconds. Okay, so for a simple harmonic oscillator, its acceleration at the extreme position is 1.5 meter per second. So, and we know that I put a show it on a table, the acceleration will be maximum at the extreme position. So it is given by maximum, that is A max at the extreme position is equal to omega squared A. So that is equal to 1.5 meter per second squared. And the speed at the equilibrium position, that also maximum speed occurs at the equilibrium position. I gave it on a table. So that is V max, that happens at the equilibrium position, that is A omega or omega A. So omega A, we can write omega A, that is 0.5 meter per second. Okay, so first part, find its period of oscillation. So by using these two data, we need to find the period. So we can say this is first equation, second equation. Divide first equation by the second equation. Omega squared A over omega A, that is equal to 1.5 over 0.5. So AA will get cancelled. That's going to be omega equal to 3. That omega means 2 pi over T equal to 3. We need to find the T. T is going to be 2 pi by 3 seconds. That is 2.09 seconds. That's the period of oscillation. Second part, find the amplitude of the oscillation. So you know that omega equal 3, you found it. Substitute in the second equation, just very simple. By using the second equation, substitute omega equal 3, you will get the amplitude. So second part, from the second equation, omega A is equal to 3. We know omega equal 0.5. We know omega equal 3, so 3A equals 0.5. Find the A, you will get 0.16 meters. Okay, the fourth question, a trolley of mass 500 grams is attached to one end of a spring, and the other end of the spring is attached to a fixed point. The spring cause of the spring is 100 Newton per meter. The trolley oscillates on a horizontal plane with amplitude of 8 centimeter. Find the maximum acceleration first part. So that means we can draw a diagram something like this. 500 gram the mass, and K is equal to 100. Okay, so it's oscillating in horizontal position. So the only force acting on the unbalanced force acting on the trolley is the tension. The weight and the normal reaction balances each other. We know that according to Hooke's law, F equal Kx, x is the extension of the spring. So here extension of the spring and the displacement are the same, because when it is at the equilibrium position, the spring will have its natural length. So extension during horizontal oscillation with one spring, remember that extension and the displacement will be the same way compression and the displacement also the same. Only the vertical oscillation, when the spring hangs vertically, there will be static extension. Next question I'll do like that. But in horizontal oscillation, the displacement and the extension, or the displacement and the compression when the spring is get compressed, will be the same. So F equal Kx, according to Hooke's law, x is the extension or compression, but here that is going to be the displacement also, right? Okay, so now F max, the maximum force, that is the maximum tension occurs. Maximum tension, T max, not the time, T tension maximum occurs when the extension becomes maximum. Extension becomes maximum means that is the maximum displacement during horizontal oscillation. Maximum displacement, that is the amplitude. So F max equal to Ka, that is equal to Ma according to Newton's second law. Okay, so K is given 100, amplitude is given 8 centimeters, so 8 into 10 to the power minus 2 equal, mass is 0.5 times A. Find the maximum acceleration, A max, because this force is maximum means acceleration will be the maximum. Solve it, we will get the maximum acceleration. That will be equal to, yes, 100, yeah, that's going to be 16 meter per second square. Okay, so that's the answer for the first part. 16 meter per second square is the maximum acceleration. Second part, find the period of oscillation. So second part, we know the maximum A max, that is omega square A, that is A max equal, minus sign we don't need, omega squared A. Omega is equal to 2 pi over t. So this is going to be A max equal 2 pi over t, all things squared A. So A max we know that 16 is equal to 2 pi over t, or 4 pi squared over t squared times amplitude is 0.08 divided by 100, 0.08. Find the t from here. This is 4. That is 0.44 seconds. I got this answer by using this answer. What I got here, A max, from that I got it. Or you can use the equation given in the data sheet, t equal square root of t equal 2 pi square root of m over k. You can use that also directly. So this is one method I use it. The other method, second part, again I am doing, you can use t equal 2 pi square root of m over k. That's given in the data sheet. You can use that directly. 2 pi square root of 0.5 over 100. You will get exactly the same answer if you use this way also. This is easy I think, but anyway, I just did it by using the first answer. I got the second answer here. But you can use this directly. This equation is given in the data sheet, so you can use that directly. You will get the same answer, 0.44 seconds. Okay, so fifth question. A spring hangs vertically from support. A mass of 800 grams is attached to the lower end of the spring. Static extension of the spring is 4 centimeter. Find the spring constant. So the static extension means when you hang the spring, that's without any mass, that's going to be the natural length without any mass. We take a light springs in all questions. We take the spring as a light spring, no mass for the spring. So when you attach a mass to its end, there will be extension and the spring will be at rest. So this is the static extension. It comes to rest. So at the rest position, when it comes to rest, at rest when you consider the forces acting on the attached mass, there will be weight mg. And the static extension, if it is, we call x1, then there will be tension T is equal to kx1. So at the equilibrium position, this is going to be the equilibrium position from where the system, we say the whole system comes to rest, or the position at which the resultant force is equal to 0, that's going to be the equilibrium position. When you pull it and leave it, it will oscillate about this one. I already did all these theories, go through it when I start this lesson. So during that, T equal to kx1, that is equal to mg at the static extension, that is going to be the equilibrium position. So at the equilibrium position, kx1 is equal to mg. So we need to find the k. So k into x1 is given static extension 4 centimeter means 0.04 equal to, the mass is 800 grams, 0.80 into 9.81. Find the k, that is the spring constant. That will be 196.2 Newton per meter. Second part, find the period of oscillation. That's very simple. They have given the equation T equal 2 pi square root of m over k. So 2 pi square root of m, that is 0.8 over k, 196.2. So that will be almost 0.4 seconds. So that is 0.40. Okay, so the up to second part we did it. Now the third part, it has two parts, A part, B part. Third part, from the equilibrium position, the mass is pulled down through 3 centimeter and then release. So already the static extension is 4 centimeters. From the equilibrium position is pulled down further through 3 centimeters and then release. A part, state the amplitude of the oscillation. So remember that from the equilibrium position, if you pull, whether it's a horizontal oscillation or vertical oscillation, whatever it is, for any type of oscillator, whether it is a test tube oscillating in water or simple pendulum or trampoline, whatever it is, from the equilibrium position, if you pull or push the oscillator through a particular distance and released, during the oscillation, the distance through which you pushed will become the amplitude. So here nothing to calculate, so that's the reason the question says state. So it's pulled down from the equilibrium position through 3 centimeter and then release means A part, the answer A part, the amplitude of the oscillation will be 3 centimeter. That's all, there's nothing to work out there. Just 3 centimeter is going to be the amplitude. From the equilibrium position, through what distance you are pulling it and leaving, that distance through what you pull from the equilibrium position will become amplitude during the oscillation. Keep it in mind. Okay, beat part, that little you have to answer carefully. Find the time taken to move from the lowest position to the displacement of 2 centimeter upwards. So from the lowest position to 2 centimeter upwards, how long, what's the time? So I'll raise again and write only the B part again. Second B part again, I'll write it. I need space. Okay, so the time taken to move from the lowest position to the displacement of 3 centimeters upwards. Okay, so if you draw the spring, when the spring is at equilibrium position, this is the equilibrium position. So it was pulled down through from the equilibrium position. It was pulled further down through 4 centimeters. So this is 2 centimeters. So it's to move upwards through centimeters. The static extension is 4. So the amplitude downwards is the equilibrium position. Amplitude downwards equal to 3 centimeters. Because it's pulled further down through 3 centimeters and released. So what's the time taken to move from the lowest position, this position, to have a displacement of 2 centimeters upwards? Okay, so that means it's starting its motion from the lowest position. Then we need to find the time taken to have a displacement upwards 2 centimeters. So it's starting from the lowest position. Initially it has the extreme position, means later to find the displacement we need to use the equation x equal a cos omega t. So initially it was at the extreme position, that is position where the amplitude happens. Later the displacement is upward direction. So if I take this downward direction positive, if I take the amplitude is 3 centimeter positive, x will be from the equilibrium position upwards. It's going to be upwards, x equal 2 centimeter means it's going to be minus 2 centimeter because displacement is a vector quantity. So downward direction amplitude, if I take positive, upward direction displacement 2 centimeter means it must be minus 2. Keep it in mind. That's going to be opposite direction to downward direction. It's upward direction, opposite direction from the equilibrium position. So x I should put minus 2 is equal to a 3, the amplitude is 3 because it's pulled 3 centimeter from the equilibrium position. So 3 cos omega, that is 2 pi over. We found the time period already. We found it. Time period we got it as 0.40 into t. Solve it, you will get the time. That's the time answer. Calculator must be in radian mode when you solve it. Solve by using calculator, you will get the time. That's the time taken to move from the lowest position where the amplitude is 3 to displacement 2 centimeter upward direction. The minus sign comes because we took the downward amplitude positive, means displacement upwards, it should be minus. Yeah, the time is the time taken for this oscillation is 0.146 seconds or 15 seconds if you want to give it in 2 decimal points. Okay, so the sixth question, a mass of 600 gram is attached to a vertical spring and then it is displaced through 8 centimeter from the equilibrium position. So that means 8 centimeter is going to be the amplitude of oscillation. From the equilibrium position, if you pull or push whatever it is through a particular distance and release, that's going to be the amplitude. So amplitude is 8 centimeters. During the oscillations, maximum speed is 76 centimeter per second. That means at the equilibrium position, the speed is 76 centimeter per second. Find the spring constant of the spring. Okay, so we know the V max and we know the amplitude. So first part answer, we know that V max is equal to A omega, and we know that omega is equal to 2 pi over T, and also we know that T equal 2 pi square root of M over K. Okay, substitute all these things. V max is equal to A omega, we can say 2 pi over T, T equal 2 pi square root of M over K, means you substitute that, you will get A into square root of K over M. Okay, so from this V max we know that 76 centimeter means 0.76 meter per second. Amplitude, that's going to be 8 centimeter means 0.08. I could have kept both centimeter, no problem. Both sides will get cancelled. The 100 doesn't matter. I converted to meter. Into square root of K is the question. Mass is 600, 0.6. Solve it and find the K. That is K equal 54.15 Newton per meter. That's right. Okay. Second part, find the maximum acceleration. So maximum acceleration means A max equal omega squared A. Nothing you can find simply. I'll do that. So second part, A max equal omega squared A. Omega equal 2 pi over T all things squared into A. So from this, A max equal 2 pi over the time period, we found it in the first part, that is okay, we have to find the time period. We'll find omega first. That's easy. Omega equal 2 pi over T, it's given in the data sheet. T equal 2 pi square root of M over K, it's given in the data sheet. 2 pi square root of M over K is given in the data sheet. So if you substitute omega equal 2 pi over T, that is 2 pi square root of M over K. So it's going to be square root of K over M, that is omega. Right, so we'll substitute that in this equation. A max equal omega squared A, we'll use that way, omega squared A. So A max is equal to omega squared means K over M. Omega squared means K over M into A. So K we found it in the previous part, that is 54.15. Mass is 0.60. Amplitude 0.08. This much of meter per second squared. Solve it, you will get the answer. That is 7.21. So the third part, find time taken to move from the highest position. Highest position means the displacement from the equilibrium position is the maximum, means at the position where the displacement is equal to amplitude, which is 8 centimeter. From the highest point to the displacement of 5 centimeter downward. So it's moving from, if I show it on a block diagram, if I say this is the equilibrium position, this is the equilibrium position, highest position somewhere here, this is amplitude, that is 8 centimeter. From this position, from here to a displacement of downwards, which is 5 centimeter. So initially here, if I take t equals 0 here, if I take initially at this, so the time taken to move from here to here, is it? So if I take t equals 0 here, how long will it take to move from here to here is the question. So if I take from here to here, I'm going to consider the motion. So t equals 0, initially it is at a position, maximum displacement at the highest position. So t equals 0 if it is at the extreme position, x equal a cos omega t. So we can say x equal a cos omega t, I should say, I should use. A is the amplitude upward direction. So displacement downwards means it's going to be minus 5 is equal to 8. Both can be centimeter, even if I convert to meter, they will get cancelled. So minus 5 because displacement downwards, amplitude upward, which is 8. So minus 5 equal 8 cos omega. Omega we found it in the previous question, that is omega equal 2 pi over t. Or you can say omega, you can find it separately if you want. Omega equals square root of k over m. You can find the omega and substitute omega and find the time. You will get the final answer. Okay, so the answer will be substitute. We will find omega first. That is going to be square root of k. We found it 54.15 over 0.60. That's going to be 9.5 radian per second. So here we'll say minus 5 equal 8 cos 9.5 t. We need to find the time. Keep the calculator in radian mode and find it. Time is 0.236 seconds. Okay, so the last part, find the speed of the mass when the displacement is 5 centimeter downward. So that is at this position, but you found the time taken to have 5 centimeter downward. So when it comes to this position, what is the speed? That's a question. So same diagram I can use. So this is the fourth part. I need to find the speed at this position. So in the theory I told that if the displacement is given by x equal a cos omega t, the relevant speed equation v equal a omega sin omega t, there will be minus sign, minus a omega sin omega t, but when we consider speed, the minus sign won't be there because we are dealing with magnitude. So the speed is given by, if the displacement is given by x equal a cos omega t, we are using this displacement. So the relevant speed is, if the displacement I am using this equation, so the relevant speed is going to be a omega sin omega t. The time I should substitute 0.236 seconds. So v is equal to a omega sin omega t. When I actually when I differentiate this, there will be minus sign, but that minus sign we are not using because we are dealing with speed. So a omega, a is 0.08, omega we found it 9.5, sin 9.5 into the time 0.236. So that's the speed at the position 5 centimeter when the displacement is 5 centimeter below the equilibrium position. I gave it in the notes. If the x is given by x equal a cos omega t, the relevant speed is a omega sin omega t. If the displacement is, we are using x equal a sin omega t, the speed will be a omega cos omega t. If you solve, you will get 0.596 meter per second. That is 59.6 centimeter per second. Those who are doing further maths, M3, you might think, why are we using this way? Can't we use b squared equal omega squared in a squared minus x squared? But that is not in the syllabus. That's the reason I didn't use it. But if you are using that equation, so this is correct, 59.6. But due to the approximations of the this one, it could be slightly different when I use the next method, but don't do that method in the physics paper because that equation is not given in your syllabus. But anyway, I'll show that. This is one method. This is the way you have to do in physics. So you have to find the relevant time for that particular displacement, then use the equation for the speed. You will get this answer 0.596 meter per second or 59.6 centimeter per second. But you can do this way also. those who are doing for the max M3, you know that there's another equation that relates the displacement and the speed, that is v squared equal omega squared into a squared minus x squared. But this equation is not in the syllabus, but I'll show that. Omega squared we found 9.5 squared, 0.08 squared minus 0.05 displacement. Solve it. From here you will get slightly different answer, that you will get 0.593. Earlier I got 596. This you will get 0.593 meter per second. That is 59.3 centimeter per second. Earlier I got 59.6. Slight different because of the time what I found, I approximated. But better don't do this method in physics. This equation is not given in your data sheet, not used in physics. Okay, so the theory related to this type of question: a spring trolley attached to two springs and oscillating such that the spring is always under tension. I already did it. See, the timestamps are given, so according to the timestamps, go through the video. So there I derived the equation when a spring is attached, when a trolley or an object is attached to two springs, and I got the equation for the time period. There I got the equation T equal 2 pi square root of m over 2k. I told that m over 2k. If the spring constants are different, k1, k2, then it will become m over k1 plus k2. How to derive it? I already did it, so I am not doing it again. So see the video. The timestamp is given. From the timestamp, you can navigate to the relevant theory. Okay, so 2 pi square root of, the asking to find the time period. So m is 900, 0.90 over 2 times spring constant of each spring is 120. Substitute, you will get the answer. .385. Okay, second part, find the maximum speed. Same way, V max equal A omega, omega equal 2 pi over T. Okay, so their amplitude 4 centimeters, 0.04 into 2 pi over T is 0.385. This much of meter per second. So that is 0.653. That's the maximum speed. Okay, next topic is motion graphs for simple harmonic motion. So the motion graphs means displacement time graph. You know, displacement is always measured from the equilibrium point. So displacement time graph, velocity time graph, and acceleration time graph. These are the three graphs related to simple harmonic motion I am going to discuss now. You know that displacement is given in terms of either cos or sine. It's a cos function or sine function. Already we did questions also based on that. When you differentiate displacement with respect to time, you will get the velocity. So if the displacement is given in terms of x equal a cos omega t, if you differentiate it, differentiation is not in your syllabus, but you should remember, if the displacement is given by x equal a cos omega t, then the velocity will be given by minus a omega sine omega t. So this, if it is cos, it will become sine. Anyway, so displacement, velocity, both are the similar shape, but only there will be a phase shift. There will be a phase shift of 90 degree. Anyway, same way we can say, if the x is given by x equal a sine omega t, then the velocity will be given by a omega cos omega t. Acceleration is given by a is equal to minus omega squared x, or you can differentiate this again. Either way, we can a equal minus omega squared x. For x, you can substitute this one, or you can differentiate this again. You will get minus a omega squared cos omega t. Same way here, you will get a is equal to a omega squared minus a omega squared sine omega t. Okay, so In the exam, what happened? They give either displacement time graph and ask you to draw the relevant velocity time graph and acceleration time graph, or they can give velocity time graph and I can ask you to draw the relevant displacement time graph and acceleration time graph. Same way they can give acceleration time graph and ask you to draw the relevant both velocity time graph and displacement time graph. So actually when we teach, we don't follow this sine cos format. The graph what they are going to give in the exam is a sine or cosine shape, whatever it is, with the different phase changes, whatever it is. But how to draw the other two graphs? If they give, for example, if they give displacement time graph, how to draw the relevant velocity time graph and acceleration time graph? There's a small technique by shifting the y-axis. Different teachers, they teach in different way. Some teachers, they tell or they teach by shifting the graph towards left or right. I normally teach by shifting the y-axis towards left or right through t by 4. I'll teach you now. So that's a simple way. Remember the method so you can answer or you can draw any graph when one of the graph is given. So it's a very simple technique you need to remember. Shifting the y-axis. Okay, so this is the technique. When displacement time graph is given, xt graph is given, and when they ask to draw the relevant velocity time graph, shift the y-axis of the given displacement time graph through t by 4 towards right. So this arrow indicates towards right. So shift the y-axis, or the y-axis means the displacement axis, display y-axis, the y-axis of the graph. Shift it towards right through t by 4 y-axis. Towards right, this arrow indicates towards right. Through t by 4, if you shift it towards right through t by 4, you will get the relevant velocity time graph. Whatever the displacement time graph, it should start from 0 or somewhere else, wherever it starts, we don't need to care. But when the displacement time graph is given, and if they ask to draw the relevant velocity time graph, shift the y-axis towards right through t by 4, that will be the velocity time graph. I'll show you a graph now. A displacement time graph is given like this. A displacement time graph is given like this. Any shape, this is true. This is displacement time graph. Okay, to get the velocity time graph, shift the y-axis towards right. That means if I put the y-axis here, if I put the y-axis here, that will become velocity time graph. That means the displacement time graph is here, starting from 0 here. If I shift the y-axis of the displacement time graph towards right through t by 4, you know this is one time period, half the time t by 2, this is t by 4. Shift the y-axis towards right through t by 4, then this graph will be the velocity time graph. So normally they ask you to draw it on the same axis. So if you want to draw the same axis, you can draw like this. You can put the dotted line normally to draw the graph easily. If you want, you can draw separate. Then I'll draw the both way, draw down. And how do they ask in the exam? Sometimes they ask to draw it separate axis they give, or sometimes they ask to draw it on the same axis. If they ask to draw it on the same axis, the given axis, how to draw the velocity time graph? Okay, so I told you I had to shift it to the right velocity. So that means if I shift it towards right, the relevant velocity time graph will start from the maximum. Here this is going to be the maximum. Velocity is going to be maximum when the displacement is equal to 0. So you should draw the velocity time graph like this. So the velocity time graph will be like this, because different units, because displacement is meter, velocity time graph will meter per second. So don't worry about the numerical value, the magnitude of the velocity. I'm going to draw only the shape of it. So when I draw the shape of it, it should start from the 0. It's not necessary to start at the same level. You can draw it even down or even up. Doesn't matter, because I already told we are not considering the magnitude, only the shape we are going to consider. So the graph should be somewhere like this. That means it should be shifted y-axis towards right, you will get this shape. This blue color graph is the relevant velocity time graph. If I shift the y-axis of the given black color, that is the displacement time graph towards right through t by 4. The shape what I observe will be the velocity time graph. So I started from the t equals 0. So on the given axis, so it's going to be like this shape. I can draw the same blue color graph separately down. Now I'll remove this blue color graph, that's the velocity time graph. This is going to be the velocity time graph. And I'll draw it separately down. Okay, before starting separately, I'll draw all three graphs on the same axis and then again I'll draw it separately. So this is the given displacement time graph. So the blue color is the given the what you drew the velocity time graph. So acceleration time graph, how to draw? If you want to draw the acceleration time graph from the given velocity time graph, again shift the y-axis of the velocity time graph towards right, y-axis shift it towards right through t by 4. T by 4, you will get the velocity time graph. So if you are drawing the acceleration time graph, if you want to draw the acceleration time graph from velocity time graph, shift the y-axis of the velocity time graph towards right through t by 4, you will get the acceleration time graph. I'll show that. Or if you want to draw the acceleration time graph directly from the displacement time graph, invert the graph. Just invert it about the time axis. So you will get the relevant acceleration time graph. Invert the graph, you will get the acceleration time graph. So we'll see whether it's become inverted graph when I shift the y-axis of the velocity time graph towards right through t by 4. So I know the blue color graph is the velocity time graph. If I shift the y-axis of the blue color graph towards right through t by 4, I should draw the acceleration axis here. The acceleration axis should be drawn here. If I draw the acceleration axis here, that will be this graph. Now what you see as a blue color graph will be the acceleration time graph. So this is the blue color is the velocity time graph. Its y-axis, if you shift it towards right through t by 4, whatever you shape, you see it's starting from 0 when time equals 0. That is going to be the acceleration time graph. So I'll draw the acceleration time graph on the same axis if I draw it. So that means this y-axis should be shifted to the right. Means I should start from here. I should start from here, the acceleration time graph. I'll draw the y vertical line. So the acceleration time graph should be this shape. Here also I don't consider the magnitude because different unit is meter per second square, but I'm drawing only the shape. So that the acceleration time graph will be like this shape. You can see the red color graph, that is the acceleration time graph. This acceleration time graph and the displacement time graph are inverted graph. When the displacement is maximum, acceleration is negative maximum. When the displacement is negative maximum, acceleration is positive maximum. You can see it's inverted graph. That is going to be the acceleration time graph. So I'll draw them separately, one by one, one after other now. Okay, so how to draw the velocity time graph and acceleration time graph for this given displacement time graph? Shift the y-axis towards right through t by 4. So the velocity time graph should start from here. Then it's a proper similar shape, sine or cosine shape. So if you draw it, start from maximum, it's going to be like this. The graph will be like this. Okay, it should be there. Here the gap is little increased, it's okay. You better draw it on the board. So that is going to be the velocity time graph. So acceleration time graph, you can invert the displacement time graph about xi. So this will come down, this will go up, this will come down. Or shift the y-axis of the velocity time graph towards right through t by 4. It should start like this. So it should start like this. You can see inverted graph of the displacement time graph is the acceleration time graph. Okay, so how to draw the other way? If the displacement velocity time graph is given, how to draw the displacement time graph? Shift the y-axis towards left. If you shift the y-axis towards left through t by 4, you will see if I shift it towards t by 4, this maximum should become 0 here. So that will be the relevant displacement time. You can see it starting from 0, see it starting from 0. So it's easy to remember. To sketch the displacement time graph from velocity time graph, shift the y-axis of the velocity time graph towards left through t by 4. Same way to draw the velocity time graph from acceleration time graph, shift the y-axis of the acceleration time graph towards left through t by 4. So you can see if I shift the acceleration time graph, its y-axis towards left through t by 4. So through t by 4 means it should be shifted somewhere here. If I shift it towards here, this graph will be extended to this way. So you'll get the display starting from here. You can see that is the velocity time graph. To draw the velocity time graph from acceleration time graph, shift the y-axis. This is the acceleration time graph. Shift the y-axis towards left through t by 4. The graph will start like this. You can see it starting like this. So easily remember, you can to draw from the acceleration time graph, if you want to draw the velocity time graph, shift the y-axis towards left through t by 4, 1/4 of the period. You will get the velocity time graph. To draw the displacement time graph from the velocity time graph, again shift the y-axis of the velocity time graph towards left through t by 4. You will get the displacement time graph. To get the displacement time graph from the acceleration time graph, again invert the graph, invert about the time axis, invert the acceleration time graph. You can see if I invert the acceleration time graph, goes up, goes down, goes up, you will get the relevant displacement time graph. Okay, we'll do a question related to this. Okay, so the question is velocity time graph is given. You need to draw the relevant displacement time graph and acceleration time graph for this given velocity time graph of a simple harmonic motion. Okay, we'll start. First, we'll draw displacement time graph. So what should we do? To draw or sketch the displacement time graph from velocity time graph, shift the y-axis of the velocity time graph towards left through t by 4 and see what could be the shape. If I shift the y-axis of velocity time graph towards left through t by 4, and if I imagine if the graph is continued towards left through t by 4, the shape will be like this. So my graph will start from the negative maximum, then I'll proceed the similar shape beyond that. So the graph is going to be start from here. So the graph will be this will be the relevant displacement time graph for the given velocity time graph. Same level I should start here. Okay, drawing on the board will be difficult. It's okay, but this is the shape you should draw for the given velocity time graph. This is the displacement time graph. Okay, how to draw the acceleration time graph for this given velocity time graph? So that the acceleration time graph I need to draw from the velocity time graph. Given velocity time graph means shift the y-axis towards right through t by 4, you will get the acceleration time graph. Or you have already drawn the displacement time graph, invert the displacement time graph about the time axis, you will get the acceleration time graph. Either way you can draw the acceleration time graph. So if I, for example, I'll check both methods. If I shift the y-axis of the velocity time graph towards right through t by 4, I'll start here. If I shift it towards right, so if the y-axis of the velocity time graph shifted to the right, means here the y-axis should come. So the acceleration time graph should start from the maximum. So it should start from here. Or invert the displacement time graph about the time axis. Here also this will start from here. So I know the shape. So it's going to be this shape. Difficult to draw a sine shape on the board, but anyway. This is the shape you expected shape for the acceleration time graph. Okay, I hope you can answer or you can draw any two when one of the one of the motion graph for S.h.m. Simple harmonic motion is given. Okay, it's an experiment how to measure the gravitational acceleration G by using simple pendulum. So there you need to have a simple pendulum with variable length. That means the length of the string attached to a small bob is called simple pendulum. Normally we attach it on a retort stand and keep a ruler behind it. It's like this. You can have a setup with a retort stand. There you can have a ruler behind it. So you have to hang the simple pendulum. So I'm not drawing everything set up, difficult to draw, but the idea we keep a ruler with a set square to measure the length of the string. I'll just draw only the block diagram. So if I draw, that's easy to draw the block diagram. So there must be a ruler to measure the length, and there must be a pointer to show the equilibrium. You can use even a pen attached to a retort stand as a pointer when it is at rest. Then the length must be measured by using a ruler with a set square. The length of the string L, it should be allowed to oscillate through small angle, because the equation what we learned, T equal 2 pi square root of L over G, is valid only for small oscillations, because I showed the derivation there. We are taking sin theta equal to theta. That's true only when the angle is smaller, somewhere less than 10 degree. Then only sin theta will be equal to theta in radians. By using that only we got that equation, T equal 2 pi square root of L over G. Okay, so let it oscillate through smaller angle, and for a given length, measure the time taken for 10 oscillations. Then repeat the experiment 3 times for the same length. Measure the total time taken for 10 oscillations. So find the average time for 10 oscillations by using the 3 different measurements taken for 10 oscillations. Then divide the average time by 10. You will get the time period of oscillation for the first length L1. So you can tabulate simple experiment. It won't take much time and do it in the laboratory at school. So you need to vary the length L, time period for 10 oscillation. So there you can have T1, T2, T3, then average time, T average. Divide that average time by 10, you will get you can measure for 15. That will be more accurate when you measure for 15. Larger time, smaller percentage uncertainty. So measure the time for 15 oscillations, T1, T2, T3, and find the average time of those 3 readings. Then T average divided by 15 gives the time period. So do it for different length. You can start from 1 meter, or depending on the retort stand that you have, the height. It will take at least 10 different readings for different lengths, and find the relevant time period of oscillation for each length, as I already showed how to take the average time period. Okay, so we have the equation T equal 2 pi square root of L over G. That is T squared. After you plot the graph, I will tell you. T squared equal to 4 pi squared L over G. We are going to plot a graph. That is T squared is equal to 4 pi squared over G into L. Okay, so you are going to plot a graph of length against T squared. T squared you get it from the time period. When you square it, you can have the T squared. So if you want, you can have a separate column for T squared also. Right, so you are going to plot a graph of T squared against length L. So it's in the form of y is equal to mx. So you'll get a graph straight line through the origin. This is L. This is T squared. The graph will be a straight line through the origin. Draw the best fit line. Find the gradient of the graph. So the gradient of the graph, find it from it by take two clear points and find the gradient. Then gradient m is equal to 4 pi squared over g. So g will be equal to 4 pi squared over gradient. That will be the gravitational acceleration. Is t squared, sorry, t squared. Okay, so the next topic is energy transfers during oscillation in a simple harmonic mode. We are learning about simple harmonic motion. So energy transfer, what type of energy transfer occurs during oscillation of simple pendulum? First we'll think that way. Okay, so it's actually nothing. Already you learned this related to this in unit 1 also. A simple pendulum means a string which has a length L carries a small bob. The mass we don't consider because period of oscillation t equal 2 pi square root of L over G given in the data sheet, equation sheet. And this equation is valid only when the angle theta is very small. Very small means when theta less than here we can say the theta less than almost 9 degree or 10 degree, we can say approximately, where sine theta equal to theta in radians. So we need to get that relationship sine theta equal to theta in radians when we are deriving this equation. I already derived it, see that. That's the reason we say this equation is valid only for small oscillations. Okay, so for small oscillation, when the bob of mass m moves from this time period does not depend on the mass. When it moves from this position to this position, what type of energy changes occurs? The energy changes occurs, it's losing the height or its height is decreasing, so that means loss in GPE. So loss in GPE means if I consider the initial height when it has a maximum displacement, so it's going to be the amplitude. So this is going to be the amplitude, this is the amplitude. So when the bob moves from here to here, loss in GPE is equal to gain in kinetic energy. So this is the maximum height, we can say h. So loss in GPE, gravitational potential energy equal to gain in kinetic energy. Loss in GPE means mgh is equal to gain in kinetic energy half mv max square, because at the lowest position the speed is the maximum. That is going to be the equilibrium position. When the simple pendulum is not oscillating, it will be at rest at this position. So this is the equilibrium position where the speed is the maximum. So half mv max square minus, if you release it from rest, initial speed is 0, half m u square. Okay, so all the masses will get cancelled. So since angle is theta is very small, we can say the amplitude, this amplitude and this, the length of the segment is almost equal to same. We know that in a circle, when you consider the circle, imagine a circle like this. In a small, like in a circle, when you consider small change in angle theta, when this theta is very small, the length of this arc, and if you draw a line between these 2 points, both will be almost same. So here we can say when theta equal less than 10, approximately the amplitude A is equal to L theta. We can say this, the length of the string is L. So L theta is actually the length of the arc, but we can say the amplitude is almost equal to length of the L theta, theta in radians. We can do that approximation for small angle. So loss in GP and GH equal to gaining kinetic energy half m V max squared minus half m u squared. I already told that V max equal to A omega. V max is equal to A omega. We can use here also for any simple pendulum. That equation is valid. Maximum speed occurs at the equilibrium position. V max equal A omega. And we know that omega equal 2 pi over T or 2 pi F. All these can be used for even simple pendulum. So this is the only change in energy. Loss in GP equal gain in KE. Same way, if it moves from this position to the other side, maximum position, somewhere it goes. Here also we can say loss in kinetic energy equal gain in GP. The height it moves up is the H gain in GP. That is the height we need to consider. That's all related to simple pendulum energy transfer. Okay, a question related to energy change in simple pendulum. Simple pendulum of length 10 meters is pulled to a side through an angle of 9 degrees. So angle of 9 degrees, we can take a small angle. So this is 9 degree from the equilibrium position. So this is the equilibrium position. The length is 10 meters. The length of the simple pendulum is 10 meters. And then released. During its oscillation, find the maximum height that the bob reaches above the equilibrium position. Anyway, it's going to oscillate again and again. So we assume there is no energy loss due to work done against drag force. So if we release it from, according to the law of conservation of energy, if we release it from a height h above the lowest position, it will go to the same height in this side also. So anyway, I can consider the initial height or the height to which it moves to the other side. We can say that height, the vertical height, it moves up h. Yes, if we are going to consider that vertical height it moves up is h. Okay, so there, this is the vertical height it moves up above the equilibrium position. So that's the thing I need to find. That will be same as the initial height h, because according to the law of conservation of energy, from which height I release, it will reach to the other side also the same height. Okay, so here we know the speed is maximum at the equilibrium position. We know the equilibrium position is the lowest point. There the speed is maximum, so we'll take that speed V max. So it's released from rest means initial speed is 0. Okay, so here I know that I already told if the angle is small, 9 degree, I can imagine the amplitude is this one. You know that if I connect these two center to center of the bob, that's going to be the amplitude. So this is the amplitude. So this is the amplitude. Okay, so the amplitude is almost equal to the length of the segment, this one. So we can say amplitude A and the length of the segment of this small circular part is same. Both are same. So the amplitude A, we can take A is equal to L theta. A is equal to L theta, where theta is in radians. So we can find the amplitude in that way. So the amplitude is going to be L 10 meters, that's the length of the that's a L, the length of the string, which is 10 meters. Theta, radians, we need to convert 9 degree into radians, means you know 180 degrees pi radians. So pi over 180 into 9, so that will become 1.57 meters. So the amplitude is 1.57 meters. Okay, so actually it's not exactly the same. Approximately we can say, we can say the amplitude is 1.5 meters. There's no other way of finding the amplitude here. Okay, small angle, no, we can take that way. Right, okay, so when it is released from here, there will be the maximum speed. V max equal A omega. We know that V max equal A omega. Omega equal to 2 pi over T. Also we know that T is equal to 2 pi square root of L over G when the angle of oscillation is small. Here 9 degree, we can say for 9 degrees sine 9 degree in radians is equal to sine theta. Check it, you will get almost the same answer. So sine theta equal to theta radians valid for 9 degree also. So that is 2 pi into square root of L 10 meter over 9.81. We can find the period of oscillation. So the period of oscillation will be equal to 6.34 seconds. 6.34 seconds. Okay, so we know the period. Omega equal to 2 pi over T. So V max is equal to A omega, A into omega 2 pi over T. We'll substitute. What could be the maximum speed at the lowest position? So amplitude we found it 1.57 into 2 pi over time period I found it 6.34. solving, you'll get the maximum speed that is at the lowest point. So that will be 1.56 meter per second. Okay, the question is what height will it reach? Maximum height. So this is the maximum height they want to find it, or the height that could reach on the other side. So we can say when it moves from here to here, loss in kinetic energy. Loss in kinetic energy equal to gain in gravitational potential energy. Okay, so loss in kinetic energy, half mass not given, anyway it's going to get cancelled, half mass into V max square. I'm considering the motion from lowest to the equilibrium position to the maximum position, height. So V max half m V max squared minus there the kinetic energy 0 because speed becomes 0 is equal to mgh. I need to find the h. M will get cancelled. So half into V max is 1.56 squared is equal to 9.81 into h. Find the h or h max, whatever it is. You will get the answer that will be 0.124 meters. That is 12.4 centimeter. That's the final answer. Okay, next we'll analyze what type of energy changes occurs during spring mass system, oscillation of spring mass system. So there are, firstly we think about horizontal oscillation where an object, I took it like a trolley or it can be a small sphere, it should move on a frictionless surface. Okay, a trolley of mass m is attached to a spring which has spring constant k. So when the system is at rest, the spring will be at its natural length, no compression, no extension. The trolley will be at the equilibrium position O. Then the trolley is pulled towards right through a distance and release. I already told that if you pull your trolley through 10 centimeter and then release, during the oscillation 10 centimeter will become amplitude. So you are moving it through, you are pulling the spring towards right through a particular length and release. That length will be the amplitude from which the distance through which you pull the trolley from the equilibrium position. So that's going to be the amplitude. So we'll think what will happen. When it moves from P to Q, we'll imagine a point Q here where the displacement is x. I'll mark that the displacement is x because when the spring is in horizontal position, the displacement and the extension will be the same because the spring is at its natural length. No force is acting on the spring because the trolley is at rest, the spring is at its natural length, so no force. So when you think about the position Q where the displacement is x, so the extension of the spring also x. So we'll see what could be the relationship in terms of energy when the trolley moves from P to Q. So there's no change in its height, it's moving on a horizontal table or horizontal surface. So no change in gravitational potential energy. So the only the change happens is kinetic energy, between kinetic energy and the elastic potential energy, what you learned in unit 1. Elastic potential energy is given by half k delta x squared. Delta x is the extension of compression, delta x squared, or half f delta x, but here we are going to use, this is easy to use, half k delta x squared. So when the trolley moves from P to Q, for the motion from P to Q, P to Q, when we consider loss in elastic potential energy because its extension is highest at P, so there will be large amount of elastic potential energy stored in it. When it moves from P to Q, the extension is going to decrease, so loss in elastic potential energy is equal to gain in kinetic energy. So that means half k a squared minus half k x squared. This is the extension at Q, this is the extension at P, which is amplitude, is equal to gain in kinetic energy half mv squared minus half mu squared. If the spring, if the trolley comes back to O, that's the equilibrium position, the speed will be the maximum where then x will become 0. if the trolley is released from P from rest, so U will become equal to 0. General equation. So I didn't substitute a value U 0, but if it is pulled and released, certainly initial speed is going to be 0. There we'll do a question related to this type. Okay, so this is the question related to horizontal oscillation of a spring mass system. So there the diagram is given. Mass of the trolley is 500 grams. The 500 is not clear. Mass of the trolley is 500 grams. And the spring constant is 60 Newton per meter. Trolley is pulled through 10 centimeter from the equilibrium position and then released. Find the speed of the trolley when the displacement is 4 centimeters. So you might think, can't we use any other equation other than energy? There is an equation, but we don't have that in Edexcel syllabus. That is, we can find V squared equal A squared into omega squared minus V squared. We can find this equation by using V square is equal to omega squared into A squared minus X squared we can use. But this equation we don't use in Edexcel syllabus. So the only way to find the speed by using energy equation in your syllabus. But we can use that equation also, but not in the syllabus. So I don't want to use it. You might use it in further mechanics, but not in physics. We don't use that. So we'll consider the motion from P to Q, where Q the displacement is 4 centimeter. First part 4 centimeter. Displacement 4 centimeter means extension also 4 centimeter when we consider horizontal oscillation. So consider motion from P to Q, where Q the displacement is 4 centimeter. We'll mark it here from here to here. 4 centimeter. Yeah, 4 centimeter. Right. So we consider the motion from P to Q. So they are loss in elastic potential energy. I'm answering the first part. There's second part here. Loss in elastic potential energy equal to gain in kinetic energy. Okay. So this point I'll name it Q. Right. Okay, so loss in elastic potential half, elastic potential half K delta X squared. So initially the extension is equal to the displacement, which is amplitude, half K A squared, because displacement is equal to amplitude. We are releasing from the point we are extended, half K A squared minus half K X1 squared. This is the extension at Q. This is the extension at A, which is amplitude, which is at P, amplitude, equal to half m V squared minus half m U squared. U is 0 because it's released from the maximum displacement position. So all the half will get cancelled. So K is given 60, 60 times A squared 10 centimeter 0.1 squared minus 60 into 0.04 squared. That's the extension at Q. That's the displacement also the same. The question is about find the speed when the displacement is 4 centimeter means that's the extension. Is equal to half, mass is 0.5 V squared minus 0. Solve it. You will get V is equal to 1.00 meter per second. That's the answer for first part. Okay, second part, find the maximum speed and hence find the period of oscillation. We can find the period of oscillation by using T equal to pi square root of m over k. That's given in the equation sheet. But here the question is find the maximum speed and hence. So don't use this one because they ask you to find the maximum speed, and by using the maximum speed find the period of oscillation. We can find it, not an issue. Okay, so second part I'll use the same equation, nothing. So I'll put the number 2 here. Motion from P to O now. P to O from the up to equilibrium position. Same energy equation. Same energy equation. General equation is the same, but the speed is going to be maximum because P to O is the equilibrium position, means that is the maximum speed. We know that the speed will be maximum at the equilibrium position minus half m U squared, but U is 0. So I'll say half mk x2 squared. Anyway, extension is going to be 0 at the equilibrium position here. The spring will return to its natural length. Okay, so we'll use it half time, the second part. Half k is 60 times a squared is 0.1 squared minus, the extension becomes 0, so no elastic potential energy, is equal to half, the mass is 0.5 V max squared minus 0, because initial energy, kinetic energy is 0. Find the V max from here. Find the V max. You will get V max is equal to 1.10 meter per second. We will get the maximum speed at the equilibrium position 1.10. But we know that V max is equal to A omega. That is omega equal to 2 pi over t. We know that omega equal to 2 pi over t. So here the amplitude is the distance from equilibrium position through what distance we are pulling and releasing. That's going to be the amplitude. Here the 10 centimeter is the amplitude. So we know the V max 1.10 equal. A is 0.10 in meters. Omega 2 pi over t. Find the t. That's the answer. Period of oscillation. So that's going to be 0.57 seconds. You will get the same answer when you use t equal to 2 pi square root of m over k. M is 0.5, k is 60. You will get exactly the same answer, nothing different. But I didn't do that way because the question is restricted, saying find the maximum speed and hence. So I followed that method. Okay, so again we are analyzing energy, spring mass system, how energy changes occurs during oscillation of vertical oscillation, vertical spring mass system. So when we hang a spring, initially the spring will have natural length when no mass is added to it. When you add a mass, it will extend and it will be at rest at the equilibrium position. So this is going to be the equilibrium position where it comes to rest. This is called static extension from the equilibrium position, from the natural length. The extension occurs up to the static extension. We call this is static extension. Normally we can use x1, we can put x1 here, that is the static extension. Some books they use symbol E for static extension, but anyway I use x1, that is the static extension. The mass is just attached and released, so it reaches the equilibrium position and it will be at rest. So this is going to be the equilibrium position. So that at equilibrium position, the weight of the attached mass will be balanced by the tension. So tension is Kx1 is equal to mg at the equilibrium position. Okay, so from the equilibrium position, if you pull the mass through a distance, for example 10 centimeter and release, it will oscillate about the equilibrium position. The 10 centimeter through from the equilibrium position through what distance I pull it and release, that's going to be the amplitude. So if the mass is pulled further down, so I'll draw the diagram again for that situation. So it's going to be like this, right? So it's pulled further down through an amplitude A. So this the equilibrium position is the same. So the amplitude is this one. This is the amplitude. So when the mass is released from here, it's going to move up. What type of energy changes could occur? So when it moves from the lowest position to equilibrium position, the height is increasing. So it's gaining gravitational potential energy. You know, this is the equilibrium position, so the speed will be maximum. Here it's released from rest. So kinetic energy also going to increase. But the extension of the spring here is x1, here the extension is a plus x1 is the extension. So the elastic potential energy at the lowest position is equal to half k a plus x1 squared. But here the elastic potential energy is half k x1 squared. This is larger than this. So when it moves from the lowest position P to equilibrium position O, what happens? It will lose its elastic potential energy. So what could be the energy equation that could be related, what are the energy changes occurs when it moves from the lowest position to equilibrium position? For the motion from P to O, loss in elastic potential energy equal to height is increasing, gain in gravitational potential energy, because height is increasing. Also, the speed is here 0, release from rest here the maximum speed equilibrium position plus gain in kinetic energy. So that's a law of conservation of energy. I'm using it. Something is lost is equal to total gain. You can't create or destroy energy. Energy which is lost cannot be destroyed. Energy cannot be created to gain these things. Whatever lost will be gained in different formats. So that's the energy equation we need to consider. Loss in elastic potential equal to gain in gravitational potential energy plus gain in kinetic energy. Okay, so normally in this situation we take the amplitude less than or equal to the static extension x1. That's the way the questions comes, because otherwise the spring could compress. When the spring is compressed, we don't know how much it is. It could be compressed. So when the spring is compressed, sometimes the turns of the springs might hit each other and the oscillation might be lost. So to avoid that type of problems, we normally take amplitude is less than, this amplitude is less than the static extension of the spring. So that means if the static extension is 10 centimeter, amplitude will be less than 10 centimeter. We will pull it from the equilibrium position. The distance we pull from the equilibrium position will be smaller than the static extension, and then we release. Okay, if it moves from O to a point Q, which is smaller than the static extension, which is Q, what energy equation we can write, or what type of energy changes occurs when it moves from O to Q? What's happening? When it moves from O to Q, what is happening? The extension is decreasing further, isn't it? Because at this position, extension is x1, so the elastic potential energy is half kx1 square. But when it moves from O to Q, the extension of the spring is decreasing, so it's losing the elastic potential energy. And we know that maximum speed occurs at the equilibrium position, so when it moves above O towards Q, the speed also going to decrease, so it's going to lose the kinetic energy also, but the height is increasing, gaining gravitational potential energy. So when it moves from O to Q, we can say loss in elastic potential energy plus loss in kinetic energy. Both are lost, means they are not destroyed, they are lost, and they will be converted into gain in gravitational potential energy. So whenever you get questions later this, you have to find out what type of energy is lost, or which energies are lost, which are gained. You have to identify, then substitute, you will get a correct answer. Okay, we'll do a question based on oscillation of vertical spring. We'll do a question on that. Okay, so next question, question number 10. This question is based on vertical oscillation of a spring. Light spring. Why do we say light spring? Means otherwise if the spring has mass, every turn will have mass. We need to consider their kinetic energy also. To avoid those problems, we say light spring. A light spring is suspended from a rigid support, and its free end carries a mass of 0.4 kilogram, which produces a static extension of 6 centimeter in the spring. The mass is pulled further down through 5 centimeter from the equilibrium position and then released. Find the maximum speed of the mass. Okay, the spring constant is not given. We can find it by using static extension. Okay, so there we can find the static, by using the static extension we can find the spring constant of the spring. Okay, if I draw the diagram, first part, initially the spring, I already drew it and I explained, initially the spring has natural length. So at the equilibrium position, I'll draw from the equilibrium position. So this is the equilibrium position at which there will be static. If I say natural length of the spring is this much, this is the natural length. So this is going to be the static extension. Static extension is 6 centimeters. So that is 6 centimeters static extension. This is the equilibrium position. So at equilibrium position, we can say mg is equal to kx1, where x1 is the static extension. Mass which is attached, we know that is 0.4 kilograms, so 0.4 into 9.81 is equal to k into 0.06. Find the k, that will be the spring constant. So there you will get k is equal to 65.4 Newton per meter. Then what happened? The mass is pulled further down. So its mass is pulled up to here maybe. It would have pulled further down up to here through a distance of 5 centimeters and release. So this is the equilibrium position where the static extension of 5 centimeter is pulled further down through 5 centimeter and release. The question is find the maximum speed. We know that maximum speed occurs at the equilibrium position. So if I name the equilibrium position O, this position P, so we need to consider the motion from P to O. At P, when it is at P, the extension is 11 centimeter because 6 plus 5, 11 centimeter. The displacement is 5 centimeter. That will be the amplitude because it's pulled through 5 centimeter and release means it will oscillate in simple harmonic motion with amplitude 5 centimeter. So we'll consider the motion from P to O. When we consider the motion from P to O, we can use loss in elastic potential energy equal to gain in gravitational potential energy plus gain in kinetic energy. So still I am doing the first part. So for the motion from P to O, P is the lowest position, O is the equilibrium position. Loss in elastic potential energy loss in elastic potential energy equal to gain in kinetic energy because speed is going to increase plus gain in GP okay, loss in elastic potential energy half K. The extension at the lowest position is 6 plus 5, that is 11 centimeter. So it's going to be half K, we already found it, so I'll substitute half K x squared. So K we found it, that is 65.4 into 11. 6 plus 5 is the total extension. So 11 centimeter means meter 0.11 squared minus, when it comes back to equilibrium position, so I'll write again the whole thing easy, then I'll come back to I substitute it. So half K amplitude, this is the amplitude, plus x1 A plus x1 is the static extension, half K A plus x1 all squared minus, at this position it has only the static extension half K x1 square. This is the loss in elastic potential energy when it moves from P to O. Gain in kinetic energy half mv max square, because equilibrium position we are finding, half mv max squared minus, initially the speed here is 0 because it's released, so 0 I can say, plus gain in GP mg, the height it moved from lowest position to equilibrium position is going to be amplitude, is moving through a height which is equal to amplitude mg a. Okay, we'll substitute the values. So this is half times 65.4 times a plus x1, so that is going to be 11, that is 0.11, or I can say 0.05, that's the amplitude, 0.05 plus 0.06 all things squared minus half 65.4 into x1 is 0.06 squared is equal to half into the mass is 0.4 V max squared plus mgh, mass is 0.4 9.81 into the amplitude 0.05. Okay, there are a lot of numbers. carefully solve it, you will get everything we know except Vmax. We need to find the Vmax. Solve it, you will get Vmax is equal to 0.639 meter per second. Okay, so that's a Vmax, we found it. Next we need to find the second part, hence find the period of oscillation. So hence we can find the period of oscillation by using t equal to 2 pi square root of m, okay, but the question is hence find the period of oscillation. So Vmax we know that, so I'll raise this. Vmax is equal to a omega, omega equal to 2 pi over t. From that we can find the period of oscillation. Okay, second part. Vmax is equal to a omega, at the same time omega equal 2 pi over t. So Vmax we know that 0.639 equal amplitude of oscillation is 0.05 omega 2 pi over t. Find the t, the time period of oscillation. You will get 0.49 seconds. We use t equal 2 pi square to m over k also, you will get the same answer. Okay, third part. Find the speed of the mass when the displacement is 3 centimeter upwards. Okay, for that we'll imagine the equilibrium position. So this is the equilibrium position at which it carries the mass. So we found the speed at the equilibrium position we found 0.639 meter per second. That's the maximum speed. So this is the natural length. So this is the equilibrium position. So when it is at the equilibrium position, its static extension is 6 centimeter. So this static extension is 6 centimeter. That is x1. Now it's moving from here. The speed we know 0.639. We found it. The question is find the speed when the displacement become upward. So when it comes to this position, when the displacement x becomes 3 centimeters. So when it comes to 3 centimeter, what is the speed? Here we know the Vmax. At this position, we know the Vmax. We found it already. Okay, so this is the equilibrium position we call named O. So this position, let it be Q. When the displacement becomes 3 centimeter upwards, name that position Q. Okay, we can use the equation for the motion from O to Q. So third part, for the motion from O, that is the equilibrium position, to Q, which is upwards above the equilibrium position. So when it moves from O to Q, the extension is going to decrease, so it's going to lose elastic potential energy. Also, we know the speed is maximum at the equilibrium position. When it goes up, the speed will decrease, so it's going to lose kinetic energy also. At the same time, it's going to gain gravitational potential because the height is increasing. So for the motion from O to Q, we can say loss in elastic potential energy plus loss in kinetic energy is equal to gain in gravitational potential energy. Loss in elastic potential. What's the elastic potential energy at the equilibrium position? So the elastic potential energy at the equilibrium position is equal to half k at the equilibrium position. It's going to be just only the static extension, half k x1 squared minus half k x1, that is the static extension. X1 is the extension at the equilibrium position. The extension is going to decrease by x, which is 3 centimeters, half k x1 squared, that's the extension here. Yeah, half k x1 squared is the elastic potential here. Here I need this extension, that is x1 minus x. x1 minus x all in squared plus loss in kinetic energy. Here the initial kinetic energy half m v max squared minus half m v1 square. v1 is the speed, at Q, the speed at Q is V1, let it be V1 at this position. The speed of the mass is V1 here, is equal to gain in GP mg, the height through which it's going to move from here to here is x, mgx. You write and substitute, you will get the correct answer. Check it again. Loss in elastic potential. At this position, elastic potential half k x1 squared, just the static equation. At this position, what is the elastic potential energy stored in it? Stored in, because careful, here we can't write. Some students have wrong idea. Loss in elastic potential means half k x squared. No, because since it's a square, a minus b all things squared is not equal to a squared minus b squared. So carefully you have to follow initial potential energy minus final potential energy. That is the loss in elastic potential. Initial energy minus final energy is the loss in elastic potential energy. So here the elastic potential half k x1 minus x. x1 is this one, x is the distance it moves. So the extension at this position is x1 minus x is the extension. So x1 minus x is the extension when it is at position Q. Okay, half m v max squared, that's initial kinetic energy, final kinetic energy, that's also loss in kinetic energy equal mg x. X is the height through which it's moving from here to here. Okay, so that's going to be half k 65.4 into x1 squared, that is 0.06 squared minus half into 65.4 into x1 minus x. x1 is 6 centimeters, 0.06 minus 0.03 squared plus half mv max squared, half into mass is 0.4, v max we found it, that is 0.639 squared minus half into 0.4 into v1 squared. Okay, so that's a loss in kinetic energy is equal to mgx. Mass is 0.4 into 9.81 into x is the height through which it moved is 0.03. Solve it, you will get the v1. Carefully solve it, lot of numbers. Okay, so v1 is equal to 0.511 meter per second. Okay. Okay, the common mistake is this part. That means finding the loss in elastic potential energy. Say in case this is 0.3 I told, but anyway, in case if third part, find the speed of the mass when the displacement is, for example, 4 centimeter upwards. In case if it is all 4 centimeter upwards, then it should be half k 0.06 square. That is the elastic potential energy initially. I am considering the motion from O to Q. So O is the initial point, Q is the final point. The elastic potential energy initially is half k 0.06 square. Elastic potential finally when it is at Q, what is the elastic potential means? That is depending on the amount of extension. So the extension, this is the extension when it is at that position. So that is 6 centimeter minus 4 centimeter. Just change the question in case if there is a question like 4 centimeter means the extension will be 2 centimeter. The extension is going to be 2 centimeter. Delta x, I can say delta x equal to 2 centimeter. So that means you will get it half k, the extension, that is 2 centimeters. So it should be half into 65.4 into 0.02 square is the energy stored on it when it is at Q. So this should be 0.06 minus 0.04 square. That is the elastic potential loss. So this initial elastic potential energy minus final elastic potential energy. The very common mistake students they make, say in case if it is like moving from the lowest position to Q, and if the extension decreases by 4 centimeter, they just put loss in elastic potential energy equal to half k loss in extension. That is wrong. Loss in extension square is wrong because initial potential elastic potential minus final elastic potential energy, that gives the loss in elastic potential energy. Never gives half K loss in extension, all things square, won't give the loss in elastic potential. Careful, it's a very common mistake students make normally. Okay, so the next topic is natural frequency. What do you mean by natural frequency? Now, when you allow a system to oscillate in its own without any external interference, then it will oscillate at the frequency called natural frequency. Where a system is allowed to oscillate in its own freely, the frequency at which it oscillates is called natural frequency. Where a system is allowed to oscillate freely, the frequency at which it oscillates is called natural frequency. For example, we know that frequency and period of oscillation are related by f equal 1 over t. Already we know that for a simple pendulum, the period is given by t equal to pi square root of L over g. So this is the period of oscillation when the simple pendulum oscillates freely without any external force or external interference. Just you pull the pop and leave it through small angle of oscillation. This is the period of oscillation. So the natural frequency, normally denoted by f naught, that's the general notation we use. So f naught is equal to 1 over t. That is 1 over t. So for a simple pendulum, the natural frequency is equal to 1 over t, means 1 over 2 pi square root of g over L. Same way, for a spring mass system, the period of oscillation given in the data sheet 2 pi square root of m over k. So the natural frequency f naught, again 1 over t. So that will be 1 over 2 pi square root of k over m. This is the natural frequency of spring mass system. Okay, what is forced oscillation? Forced oscillation means forcing an oscillator. Oscillator means system that can oscillate is called oscillator. Forcing an oscillator to vibrate or oscillate according to frequency of an external vibrator is called forced oscillation. Forcing an oscillator or forcing a system to oscillate according to the frequency of external vibrator or external system is called forced oscillation. For example, you can have in the laboratory we create forced oscillation by connecting a spring mass system. A spring mass system, if you let it oscillate, it lost frequency, the natural frequency equal, I just wrote it, f equal 1 over 2 pi square root of k over m. But if you connect this spring mass system to an electrical vibrator, so electrical vibrator which has variable frequency of oscillation that we can obtain by using a signal generator. Say for example, if signal generator, you know that it's a AC output, it's a AC generator, AC voltage, but the frequency could be changed. So if the frequency of the AC output of the signal generator, for example 20 Hertz, the electrical vibrator will vibrate up and down. This electrical vibrator will vibrate at 20 Hertz. So the spring mass system also will vibrate at 20 Hertz. The same frequency as the electrical vibrator, it will vibrate. Now you change the output of the signal generator to 40 Hertz. So the electrical vibrator will vibrate at 40 Hertz. So the spring mass system also will be forced to vibrate at 40 Hertz. This is called an example for forced oscillation. But naturally that happens. When your car passes over bumps, you know the mirror, everything, they vibrate according to the frequency of the wheels at which they are passing over the bumps. Or maybe due to the vibration of the engine of the car, the mirror can vibrate. Or during earthquake, the buildings are forced to oscillate at the frequency of the tremor. During washing machine also, at this due to the depending on the frequency of rotation of the drum, the washing machine will be forced to vibrate at the same frequency. These all are the examples of forced oscillation. So the forced oscillation means a system that can oscillate in its own freely also, but it is forced to oscillate according to the frequency of external vibrator. This type of oscillation is called forced oscillation. Remember that during forced oscillation, the driven system, for example, this is the driven system, spring mass system is the driven system, or your car in the car, I told the mirror can vibrate at the frequency of the engine. So mirror system, the mirror, the arm, everything together, it's a driven system. Same way, a washing machine is the driven system. It's forced to oscillate at the frequency of the rotation of the drum. So during forced oscillation, the driven system will always oscillate or vibrate at the frequency of the driver. This is called driver, the frequency of the electrical vibrator, that's called frequency of the driver. So always remember that frequency of the driven system will be equal to frequency of the driver. That you must know that. The next topic is resonance. What is resonance? Okay, that is something related to forced oscillation. Resonance happens during forced oscillation. So I told that we can force an oscillator according to the frequency of external vibrator. But when the frequency of the external vibrator becomes equal to natural frequency of the driven system, what happens actually? Say for example, think about simple example, a swing or maybe a mass attached to say it's like a simple pendulum. It has natural frequency on the time period t equal to 2 pi square root of L over G. So imagine if you pull this pendulum, the bob to here, some position here, a small angle, and you are leaving it. So the time taken by this bob, we assume there is no energy loss due to drag force. So the time period taken by the bob to move from here to here, then to come back is t equal 2 pi square root of L over G. Now when it comes back to this position, the time taken is this amount. You are applying a force to it. Just means you are giving a push. That means you are transferring energy to it. We are doing work on it. Small work is done. When the, say for example, you just pull the bob and release it. It's moving. Now it's coming back. The time taken is this one. So when it comes back, you are just giving a small push to it. You are doing a small work. You are transferring a small amount of energy to it. What happened? Now it's getting energy. So it will go further, more amplitude. It will move with large amplitude. But this equation does not depend in amplitude if the oscillation is within 10 degree, small oscillation. Now it has gained energy. So it's moving with large amplitude. To come back again, from the moment you give a small energy transfer, from that moment to come back, it takes same time again, because this time period does not depend on the amplitude. So when it comes back, again you are giving additional energy. It will move with further extension or further amplitude. The amplitude will increase further. That means every time when it comes back, you give energy. So the time interval you are taking to transfer energy is equal to time period of oscillation. Time period at which you are transferring energy to the system, the simple pendulum, is same as the time period of oscillation of the simple pendulum. So the energy is transferred at the same period as the time period of oscillation. Means the frequency at which you are transferring energy is same as the natural frequency of the oscillation of the system. So what's happening here? You are transferring energy at the frequency which is equal to natural frequency of the system. Means you are forcing it to oscillate at your frequency by transferring energy. The frequency at which you are transferring energy is same as the natural frequency of simple pendulum or the system. Means you observe that the amplitude is increasing. Why? The energy is transferred more efficiently. I can use that word. Energy is transferred more efficiently when the frequency at which you transfer energy becomes equal to natural frequency of the simple pendulum. I hope you understood. Say for example, if you change the frequency at which you transfer energy, say for example, you are trying to give it more faster, more quicker, right? So imagine this bob is moving and coming back. Somewhere when it is here, you are trying to give the energy. Sometimes you get, when the bob is on the way, it's moving here, it has kinetic energy. This direction, it hasn't reached the maximum amplitude percent. So the bob is somewhere here, still moving this way. You are just pushing it, same as earlier what you did here. Then the bob might stop. The oscillation might be disturbed. So the energy transfer is not efficient. The amplitude might decrease. Okay, so to have a good increase in amplitude, the time period at which you are transferring energy must be same as the time period of oscillation of the system. Other way, if I say the frequency at which you are transferring energy must be same as the natural frequency of oscillation of the system. When you transfer at that rate, the energy transfer will be more efficient, the amplitude will increase. This is called resonance. Okay, this is called resonance. Okay, so several times the past paper they asked what is resonance. So how do we define? You understood you have got the picture. This is I just took an example of oscillation of a simple pendulum. The same thing is true for electrical vibrator also. When you think about electrical vibrator with a spring mass system, here also the whole system is oscillating. Here also the electrical vibrator is vibrating, forcing the spring mass system to oscillate. There also the same idea. The vibrator, when it has the period of transfer of energy, vibration means transferring energy. It's a vibration, is it? So during the vibration, the spring mass system is gaining energy from the vibrator. Here also, if the time period at which it's transferring energy is equal to actual time period of oscillation of the spring mass system, which is 2 pi square root of m t equal to 2 pi square m over k, then the energy will be transferred more effectively or more efficiently. The energy will be transferred. There are other way, if I say, if the frequency of the electrical vibrator becomes equal to, electrical vibrator is transferring energy, is it? So the frequency of the electrical vibrator becomes equal to natural frequency of the spring mass system. What will happen? There also energy will be transferred more efficiently. That is called resonance. So it will oscillate with large amplitude. So you know the idea of what is the meaning of resonance. That question is asked several times in the past paper. Resonance means, this is the way you should answer, when the frequency of the driver is my and I am transferring energy. Here the frequency of the driver, that is the electrical vibrator, frequency of the electrical vibrator. So this is the answer. When the frequency of the driver becomes equal to natural frequency of the driven system, maximum amount of energy will be transferred from the driver to the driven system, and the driven system will oscillate with large amplitude. This is called resonance. So I explained why it oscillates with large amplitude. Means more efficient transfer of energy causes the increase in amplitude. I hope you understood now. Okay, so this is an external evidence for resonance. That means the resonance occurs when the frequency of the driver becomes equal to natural frequency of the driven system. To show that, we can use this experiment. So there's an electrical vibrator. It's connected to a signal generator. Signal generator is an instrument that gives out AC voltage, but the frequency of the AC voltage is adjusted. You can change the frequency of the AC voltage. So the electrical vibrator will vibrate at the frequency of the output of the signal generator. So the electrical vibrator vibrates in this direction. This way it vibrates. So a spring mass system is attached to the electrical vibrator. So the spring mass system will be forced to oscillate at the frequency of the electrical vibrator. Electrical vibrator will vibrate at the frequency of output of the signal generator. You can see there's a display. In this display we can see the frequency of output voltage. You can see here. So for example, if the display shows 20 Hertz, means the output voltage is 20 Hertz. So the electrical vibrator will vibrate at 20 Hertz. Spring mass system will be forced to oscillate at the same frequency of 20 Hertz. Okay. So here there's a ruler. This is a set square to ensure the ruler is in vertical. Okay, so when there is no oscillation, a small pointer is attached to the mass. So when it is oscillates, the mass will move up and down. We can find the amplitude of oscillation by using this pointer. Okay, before you switch on the signal generator, keep the signal generator at off state and pull the mass through small distance and let it oscillate. Find the time period of oscillation, how long it takes to complete 10 oscillations or 15 oscillations. So divide the total time by, if you are measuring the total time for 15 oscillation, divide the total time of oscillation by number of oscillations, that is 15, you will get the period of oscillation. Repeat this experiment 3 times and find the average period of oscillation you know that experimentally, 1 over T is the natural frequency of the spring mass system. So find the F naught, natural frequency of the spring mass system, find it experimentally. Okay, now switch on the electrical vibrator. And the signal generator, switch on it. So start the experiment with lower frequency of signal generator, possibly whatever the lower frequency you can get it in your signal generator, start with that, maybe 2 hertz or something like that. For that particular lower frequency of oscillation, measure the amplitude of oscillation by using the ruler. So you are going to change the frequency of the electrical vibrator, frequency of oscillation of the electrical vibrator, by changing the frequency of output signal of the signal generator. So you can tabulate it. So change the frequency of the electrical vibrator and measure the amplitude of oscillation, not the displacement, amplitude of oscillation. So you know when the point is at rest, take the reading. When it oscillates, up to what distance it moves and then turn back, record that reading, subtract this from this, you will get the amplitude. So for different frequency of oscillation of the electrical vibrator, measure the or read the corresponding or relevant amplitude of oscillation. Plot a graph. Now plot a graph of amplitude of oscillation against frequency of the electrical vibrator. That is the frequency of output of the signal generator. You can get it from the display of the signal generator. You will get a shape of graph, something like this, you will get it. That means something like a sharp, little bit sharper graph, you will get it. Okay, so now you know that the amplitude increased, then decreased. So get the relevant value which related to the maximum amplitude and get the reading from the graph. You will see this is the frequency of the signal generator, frequency of the vibrator, electrical vibrator. You will see the frequency of the vibrator when it is equal to F naught, that is the natural frequency of the string mass system, you will get the largest amplitude of oscillation. Why that happens? Energy is transferred more efficiently. That's the reason. Due to efficient transfer of energy, the amplitude increase. I already explained. So this is a good experimental evidence for resonance. Okay, so this is another experimental evidence that is called Barton's pendulum. It's simple actually, even you can do it at home. Take a string and keep it under tension with 2 supports. And there are 5 different simple pendulums attached with different lengths. P1, P2, P3, P4 have different length of strings. They are simple pendulums. P naught is another pendulum that has same length as P3. So the length of P naught, say if I say the length, this is L1, the length of this is L1, this is L2, L3, L4, and this length is L naught. The length L naught is equal to length L3. That's the way it's made, these pendulums. So both of them will have the same natural frequency. We know that the natural frequency or the time period of oscillation given by T equal 2 pi square root of L over G. So that frequency is given by F equal 1 over 2 pi square root of G over L. So both have the same length, means P0 and P3 pendulums have same length. L0 equal L3 means both of them will have the same natural frequency. Now this will be used as driver. By keeping all these pendulum at rest, all are connected to the same string which is under tension. Not much tension, but keep it little stretched. By keeping all the pendulums at rest, pull this pendulum out of the board and let it oscillate. So the pendulum not going to oscillate this way, it's going to oscillate this way, into the board, out of the board. That plane it's going to oscillate. So when it oscillates, you can see after a few seconds, all these pendulums P1, P2, P4 will show very little amount of oscillation, but P3 will oscillate with larger amplitude. It will oscillate with large amplitude. Generally, the mass of P0, the mass of the bob P0 is much larger than mass of P1, P2, P3, P4. Normally, the bobs of P1, P2, P3, P4 are made of normal cork or very light mass. This is a metal mass. So what happens when it oscillates? The string is attached to the horizontal string. So this string, the vertical string of the P0 oscillates. where it is connected to the horizontal string, so it will force the horizontal string to oscillate at the same frequency as this frequency. So this horizontal frequency, this horizontal string is oscillating at the frequency of natural frequency of P naught. So what happens? These all four pendulums will be forced to oscillate at that frequency. For example, if I say the frequency of P naught is F naught and the natural frequency of P1 is F1, this is F2, this is F3, but F3 equal F naught, so F3, but F3 is equal to F naught because same length. This is F4, the frequency, natural frequency. So since this string is attached to the horizontal string, when the pendulum P naught oscillate, this point where it is attached, that will force the horizontal string to oscillate at the frequency F naught. So all of the four strings are attached to that horizontal string. So all those pendulums are forced to oscillate at the frequency of F naught by the horizontal string. Now what will happen? This has the same natural frequency of this one. This is the driver. Frequency of the driver is equal to natural frequency of the driven system P3. P1, P2, P3, P4 all are driven systems. They are forced to oscillate, but this natural frequency equal to this frequency. So maximum amount of energy or large amount of energy will be transferred from this string to this pendulum. So this pendulum P3 will oscillate with larger amplitude. That also a good example for resonance. Okay, so next thing is damping or damped oscillation. Okay, you can see that when you pull a simple pendulum and leave it, it will oscillate. So after several oscillation, it comes to rest. But during the oscillation, the amplitude gradually decreases. Why this happens? Due to work done against friction, work done against drag force. So the losing the energy of the oscillator due to work done against the drag force causes the amplitude to decrease. This phenomena, this type of oscillation is called damping or damped oscillation. Not only due to work done against friction, if the system consists of like a ductile materials, they undergo plastic deformation during the oscillation. They absorb energy to deform and not returning the energy back. Then there will be loss of energy of the mechanical energy will be lost because there's work done to deform the plastic material, ductile material, so the amplitude will decrease. So normally they ask in the exam what is damped oscillation. So damped oscillation, you can say damping is the dissipation of energy of an oscillating system due to friction or due to plastic deformation of ductile material that causes decrease in amplitude is called damped oscillation. Easy to remember that. That is the answer you should give when they ask what is damped oscillation. Again, I'm telling. So damped oscillation means dissipation of mechanical energy of an oscillator due to friction or due to a plastic deformation of ductile material that causes reduction in the amplitude is called damped oscillation. Okay, so the damped oscillation can have different types. The most well-known oscillation is called underdamped. So there it's a repeated oscillation, but amplitude gradually decreases. There the amplitude falls on an exponential curve, something like this. If I draw a graph like this is displacement, against time. So the graph would be something like this. So the period of oscillation remains the same, very important. In this type of underdamped oscillation, the period of oscillation remains the same. The period of oscillation, this time period is same as this and this. The time period remains the same, but the amplitude here is A naught Here the amplitude is A1. Here the amplitude is A2. And here the amplitude is A3. I'll mark it here. This amplitude is A3. Okay, so the amplitude falls on an exponential curve. This is an exponential curve under damped oscillation. So in under damped, this is an exponential curve. So that type of damping shows several oscillations, but the amplitude will decrease. The amplitude will fall on an exponential curve. So there we can show that since these peaks are falling on an exponential curve, we can show that the derivation is not necessary. But remember that they might ask that the peaks are falling on exponential curve. So if they are falling on exponential curve, if the peaks are on the exponential curve, so then A naught over A1, we can derive it, but you don't need, so I am not doing it. A naught over A1, the ratio of the amplitudes must be same. A naught over A1 is equal to A1 over A2 is equal to A2 over A3 and so on. So if they ask you to show or check whether the peaks are falling on an exponential curve, find the amplitude here, read it from the graph. A naught over A1, find it. Then A1 over A2, find it. A2 over A3, if they are almost same, we can say the peaks are falling on an exponential curve. So a good example for this type of damping, simple pendulum, spring mass system, they oscillate and the amplitude gradually decreases. There are two more different types of damped oscillations. One is called critically damping, other one is called over damping. Critically damping means it won't complete even half an oscillation, even 1/4 of oscillation. It will come to the equilibrium position during very short time. So this is displacement. This is time. So if it is critically damped oscillation, critically damping, it will come to rest or come to the equilibrium position during a shorter time. If initial displacement is this much, it will come to the equilibrium position in a shorter time. It's a curve. So it comes to the equilibrium position in a shorter time. So the applications are there for this. The good application is in a analog meters, analog voltmeter and ammeter, because when you know they are in analog meters like a voltmeter ammeter, the pointer is hanging from a very sensitive, very minute spring. When you apply a voltage or when current pass through it, there's a force exerted on the coil, so the coil rotates, so the pointer turns, but it comes to rest immediately the point at which it wants to show the reading. It won't oscillate about the point. So the new equilibrium position when current flows is the position where it comes to rest, but there it immediately comes to rest without showing any oscillation. So that is the new equilibrium position. It comes to rest in a very short time and without showing any oscillation. So that is a good example for application of critically damping. Other one is over damping. Over damping is something like this. It takes longer time, but it won't show more than 1/4 of oscillation. It comes to rest, but takes longer time than this, something like this. That good example for damping of shock absorbers in vehicles, because if they come to equilibrium position in a shorter time, it can cause jerk to the passengers. So when they pass over a bump, it comes to the equilibrium position taking more time, so it can avoid unwanted jerk, shock to the passengers. So this is critically damping, this is over damping. Applications are there. Okay, so next is tuned mass damper. Now tuned mass damper means it's actually a system, it's made by two layers of maybe metal. Between that there will be a lot of springs kept. So that is called tuned mass damper, like a wafers, two metals, between that there are many springs are kept. For this system, it has a natural frequency. It's made like this. Normally they keep this tuned mass damper They are used to reduce the unwanted oscillation of overhead bridges. So it's normally kept the pillar. This is the pillar. This is the bridge. So they keep this tune mass damper somewhere between the bridge and the pillar. Between that they keep the tune mass dampers. Okay, when the vehicles goes, if there's due to some reason, if the bridge oscillates, it's made like this. The natural frequency of the bridge, in case if the bridge is oscillates, the natural frequency of the bridge is the tune mass damper has natural frequency. The natural frequency of the tune mass damper is almost equal to the natural frequency of the bridge system. So when the bridge oscillates due to the vehicle's movement, the bridges could be forced to oscillate. So when the bridge oscillates, it's resting on the tune mass damper. So the mass damper will be forced to oscillate. Then what will happen? Resonance will happen. Due to resonance, energy will be transferred from the bridge to the tune mass damper. So the bridge will lose its energy because it's transferring maximum amount of energy to the tune mass damper, because bridge and the tune mass damper have same natural frequency. So the energy will be transferred or lost or dissipated from the bridge to the tune mass dampers, and the tune mass dampers will dissipate that energy to the surrounding without transferring energy back to the bridge. They should not transfer energy back to the bridge. That's the way the technology. So they will lose the energy to the, or dissipate the energy to the surrounding without transferring energy back to the bridge. So the bridge will lose the oscillation energy, and it can reduce the amplitude of oscillation, or the oscillation could be ceased. It could be stopped by transferring energy to the tune mass damper. The basic technology is the resonance there. Both have the same natural frequency. So there's a question in the past paper, I can't remember the year. The sound produced when the drum is struck may persist for a longer time, too long, and so damping is used. Some drummers attach strips of gel to the drum membrane. This is the drum membrane or drum skin. The gel is able to deform plastically and hence shorten the time that the drum sounds. So sometimes when you beat the drum, the skin or the membrane can vibrate to longer time than the expected time. So they want to reduce the oscillation. So they put a strip of gel, and the question explains how a gel that can deform plastically is able to produce damping. Okay, so it's actually a 3-mark question. This question based on 3 marks, past paper question. Okay, what would be the answer? First, you should say when the drum when the drum skin vibrates, the gel is forced to oscillate, and gel absorbs the energy for its plastic deformation without transferring energy back to the membrane or to the skin. Therefore, energy is, now you know that energy is absorbed from the, because it's kept on the skin or the membrane. So when the membrane vibrates, the gel is forced to vibrate. So when the gel is vibrate, it will deform. The deformation is plastic, not elastic, plastic. So what is the origin, or from where the energy is used to deform the gel plastically? The energy of the vibration of the drum, the mechanical energy of the skin or the membrane of the drum is used to deform the gel plastically. It's a plastic deformation. You know, plastic deformation means permanent deformation. You learned that in Unit 1. So due to the plastic deformation, the energy will not be given back to the skin, because whenever there's a plastic deformation, energy will not be given back. It won't come back to the original shape. So the energy will not be transferred back to the skin. Therefore, the vibration of the skin will be reduced during a shorter time. So the answer, if you are giving point form, 1 mark is given for saying the gel will have plastic deformation. Plastic deformation means permanent deformation, and it will absorb energy from the skin of the drum. Since the deformation is plastic, energy will not be transferred back to the skin, and energy will be dissipated. 3rd mark, energy will be dissipated or lost from the skin. So the vibration will be stopped. That's the answer, 3 marks. Okay, next question. When a ship is sailing on a rough sea, the waves can set the ship into simple harmonic motion, S.h.m, simple harmonic motion short form. At one position on a ship, passengers experience a vertical oscillation of amplitude of 0.85 meter with a period of 6 seconds. First part, calculate the maximum acceleration of the passenger. So we know that A max is equal to omega squared A. We know A equal omega squared x, but A becomes maximum, x becomes maximum, x is maximum for amplitude. So omega squared x. So their omega is equal to 2 pi over t. We know that. So this is going to be 2 pi over t, 6 seconds, all in squared. Amplitude is given 0.85. So you will get 0.932 meter per second squared. Okay, the second part, the graph shows how the vertical displacement x of the passenger varies with time t. Add to the graph to show how the acceleration of the passenger varies over the same time. So the reference point, you don't know which one they take. But anyway, you know, in unit 1 you would have learned in displacement time graph. Any point could be taken as a reference point, but here the reference point, they are not telling it's not the equilibrium position. If they take it as equilibrium position, then the graph would have both positive and negative axis. Anyway, they would have taken some other point as a reference point when they are taking the displacement. The displacement is throughout the motion positive, but the displacement is increasing and decreasing in a shape of sine or cosine, whatever it is. But when you think about the acceleration is always towards the equilibrium position. So when the passenger goes above the equilibrium position, the acceleration should be towards the equilibrium position. Below the equilibrium position also towards, means the direction of the acceleration will become opposite each other. So there the acceleration time graph will have both positive and negative sides. Remember that. So now I already explained that to draw acceleration time graph from displacement time graph, it's exactly the inverted graph. Okay, so there, if I want to draw the displacement acceleration time graph, we'll draw the relevant the vertical lines. So it will become exactly inverted graph with respect to 0. So it will be like this. So here it's positive maximum, so it should be mirror image. If I imagine this is the equilibrium position, then if I draw the displacement diagram about equilibrium position, it will be like this, positive, negative, like this. So if I invert it about the equilibrium position, what shape I will see, that will be the shape of the acceleration time graph, inverted graph about time axis. This is the time axis. Okay, so the graph will be, this is positive, this is negative. So here, this is going to be maximum, so it's like this. This is the graph for acceleration against time. The blue color indicates acceleration time graph either side of the origin. Okay, so a passenger, third part, on the ship stands on a weighing scale. When the sea is calm, the reading on the weighing scale is 75 kilogram. No oscillation, it's calm, means when there is no oscillation, it's 75 kilogram. Draw free body force diagram for the passenger. So if I take a passenger as a small dot, I don't need to draw actual passenger. So there will be two readings, two forces acting on it. One is the weight of it pulled by the earth, that is the weight. That is mg. Then the normal reaction, that is pushed by the weighing scale on the passenger, that is pushed by weighing scale or normal reaction, that is R. Okay, that's the answer. But if you want to analyze further, what will be the reading, which force is read by the weighing scale? If I draw the weighing scale here, So weighing scale reads the push exerted by the passenger on it. So the passenger, actually the weight is the pull by earth. Earth is pulling the passenger down. The third law of air will act on earth upward direction. You learned that in unit 1. But passenger is standing on the weighing scale. So the passenger will exert a force on the weighing scale that is downward pushed by the passenger. So that is R. When the passenger pushes the weighing scale down, weighing scale push the passenger upward direction. So these two forces are the normal reaction. Weighing scale read the R. Remember that the reading of the weighing scale is R. Okay. The normal reaction on the third law pair of the normal reaction on the passenger is pushed by the passenger on the weighing scale. That will be the reading of the weighing scale. Okay, so on rough C, the ship oscillates with a large amplitude. Explain why the reading on the weighing scale will vary. So we drew the free body force diagram already for the passenger. There are two forces, the weight acting on it and the normal reaction or push by the weighing scale. The weighing scale reads the third law pair of R, or I think I can say the weighing scale reads the third law pair of R, or it reads the normal reaction, no problem. Okay, it's oscillating. So you know that. So it will have resultant force. Say for example, when there is no oscillation and the sea is calm, this is the level, we'll assume this is the level. When it is not oscillating, this is the level of the water or level of the weighing scale when the passenger stands on it at equilibrium. So imagine when the ship is at a calm sea, no oscillation. So the sea level is oscillating between this level and this level. When it is here, when the C is at here, or the weighing scale is at that, either way I can say with the C level or the weighing scale is oscillating between this position and this position. It's as oscillating up and down. When there is no oscillation, when the C is calm, the weighing scale is at this. So this is the equilibrium position. When the weighing scale is here at this position, also the two forces acting, that is mg are the two forces acting here also. When it is here also, the same two forces acting, but the magnitudes are different. We know that the oscillation of the weighing scale or the oscillation of the C is simple harmonic. So when it is here, the resultant force should be towards the equilibrium position, that is F equal ma, resultant force F equal ma. We know that if it is simple harmonic motion, always the acceleration should be towards the equilibrium position, means resultant force and acceleration are parallel vectors, mass is a scalar. So if it is a simple harmonic motion, acceleration must be towards the equilibrium position, means resultant force must be towards the equilibrium position. So when it is above the equilibrium position, these are the two forces acting. The resultant force must be towards the equilibrium position. That means mg must be greater than r. Mg must be greater than r. R is the reading, mg is the weight. Weight of the passenger never changes, that is due to pull by earth, that remains constant. So r will become smaller than mg, because mg becomes larger, means mg won't change, r changes, so r becomes smaller than mg. So the resultant, since the resultant force is towards the equilibrium position, when it is at this level below the equilibrium position, it's oscillating up and down. So there is an equilibrium position, that is this. When the weighing scale come to the lowest position, there the resultant force should be towards the equilibrium position, because acceleration must be towards the equilibrium position if the oscillation is S.h.m, simple harmonic motion. So resultant force must be towards the equilibrium position. So in that situation, mg remains constant, r becomes greater than mg. So at this position, when it is at this position above the equilibrium position, where in this one r is less than mg, so the reading will become smaller than, lower than the weight of the passenger. When the passenger is at the equilibrium position, we know that A equal minus omega squared x. X is measured from the equilibrium position. At the equilibrium position, x is 0, A is 0. A is 0 means resultant force 0. That means at the equilibrium position, the reading will be equal to mg. So at the equilibrium position, R equal mg. Reading will be equal to the actual weight of the passenger. When it is below the equilibrium position, R must be greater than mg. So the reading reading is R. I told that already. Reading is R. Reading of the weighing scale. R will become greater than mg. This is the reason for change in the reading. So you can write it. Simply, I am not writing it. You can say. First point, you can say this is actually a 3-mark question, but we can write more clearly. There are enough lines are given. You can say the weighing scale reads the third law pair of the normal reaction. You can say normal reaction of the passenger, or you can say weighing scale reads the push by the passenger, which is capital R. Then you can say when the passenger is at the equilibrium position, or when the weighing scale is at the equilibrium position, there is no resultant force. Reading will be equal to actual weight of the passenger. Then you should say always the acceleration should be towards the equilibrium position, means resultant force must be towards the equilibrium position. Therefore, when the passenger is above the equilibrium position, resultant force must be towards the equilibrium position. Therefore, R will become smaller than mg, reading will become smaller than mg. When the passenger is below the equilibrium position, also the resultant force must be towards the equilibrium position. Therefore, R will become greater than mg. The reading will become greater than mg. That's all you have to write. Okay, I wrote the answer shortly here. Weighing scale reads the push by the passenger on the scale R. So you already marked R, third law pair as that. At the equilibrium position, no acceleration, so R equal mg. So the reading will be equal to mg. Above the equilibrium position, resultant force F equal mg minus R, mg minus R, must be towards the equilibrium position. It must be towards the equilibrium position, and hence R must be less than mg. Then only the force will be towards the equilibrium position. Below the equilibrium position, also resultant force F towards the equilibrium position, which is upward, you know that. Hence F equal R minus mg. So there what happens, R should be greater than mg. So reading will become greater, reading will be equal, reading will be less. 3 positions I found it. Okay, the last part, C part, third part, C part. Whilst the passenger is standing on the weighing scale and the ship is oscillating, the maximum acceleration of the ship is 0.70 meter per second square due to oscillation, not the motion. The oscillation causes maximum acceleration of 0.70 meter per second squared. Calculate the maximum reading on the weighing scale. Already I told that when the passenger is below the equilibrium, this is the equilibrium position. When the passenger is below the equilibrium position, this is the weight, this is the normal reaction. R will be greater than mg. So the maximum reading occurs below the equilibrium position. Above the equilibrium position, reading will decrease. When it goes below the equilibrium position, reading will increase. But maximum occurs when the acceleration is maximum, because the resultant force here, F towards the equilibrium position, F is equal to R minus mg is equal to ma. So that is R is equal to mg plus ma. So R max occurs. So this is R max occurs. The reading is the maximum, means weight is constant. When the acceleration becomes maximum, m k max. You can ask me where the maximum acceleration occurs. At the extreme position, when it goes to the lowest position, maximum displacement, lower position, acceleration will be maximum. So now find it. Weight of the passenger, that is when there is no oscillation, when the sea is calm, R equal mg, because acceleration is 0 at the equilibrium position, so that is given 75 kilogram. So 75 into 9.81 plus 75 into 0.70. So R max you will get 788.3 Newton. But the reading is in kilogram. So reading in Newton, this one. So reading in kilogram means I need to convert to kilogram. 788.3 divided by 9.81 kilogram. So reading maximum. So the maximum reading I am getting 80.4 kilogram. That is the maximum reading. Okay, so that's the end of this oscillation. Is a long topic. but I think I have done everything without missing any topic. Okay, you can pass your comments. Bye.